A very good evening to all the brilliant minds gathered here today. Our respected faculty, valued corporate professionals, passionate research scholars. It gives me immense pleasure to welcome you all to the fourth day of our faculty development program on next gen technologies in action, generative AI, and quantum computing. This evening, we are truly privileged to have with us our distinguished expert, Dr. Catherine Kintrella, as our esteemed resource person. Dr. Catherine is a globally recognized, multi award winning AI and quantum computing expert, currently serving as the head of Cognizant's AI and data practice in Global Growth Market Switzerland. With an illustrious career spanning over 26 years in technology and 18 years in artificial intelligence, she has been a driving force in shaping the future of digital transformation. Dr. Catherine has held leadership roles in research and development, artificial intelligence, information technology, and data with some of the most prestigious organizations in the world, including Volkswagen Group, BMW, Mercedes, Siemens, ZF, and Bosch. Dr. Catherine has also been recognized by the World Economic Forum, where she serves as a main data and AI member of the Global Future Council and Data Foundation. Dr. Catherine's contribution beyond industry. She is a professor of AI applied to business at the Swiss School of Business and Management in Geneva, technical editor and mentor. Her pioneering work bridges cutting-edge research with real-world innovation, particularly in autonomous systems, cybersecurity, enterprise AI, and sustainable digital ecosystem. With such an outstanding portfolio of achievements and thought leadership, we are indeed fortunate to learn from her insights today. On behalf of Sadhu Vaswani Institute of Management Studies for Girls and FDP Organizing Committee, I extend a warm welcome to Dr. Catherine, and we eagerly look forward to your session on zero-day threat prediction using generative models. Ladies and gentlemen, please join in me welcoming Dr. Catherine. Over to you, ma'am.
Yes, thank you very much for the kind invitation. And
Yes,
then I'll start and just first check if you can see my presentation.
Yes, ma'am.
All right, thank you. So in this faculty program, I'm going to go ahead from what it is the use of generative AI, but this is based on the latest emerging tech in regards to quantum computing. There is a need in order then to bring this cross-cultural type of new expertise across different type of markets, but mainly in quantum computing. The main use cases are in life sciences, the banking, and cybersecurity. So there are a big, huge need in order then to build the next workforce of the future and on research on these trends, as well as the future scope in artificial intelligence. So what I'm going on here is not your typical generative AI training. I mean, I bet all of you would have a lot of them, but this is more into, well, what is the art of the possible when exploring innovations on transforming AI with quantum technology, which is the next step. So I like first then to give a very short overview, the foundations of generative AI and quantum computing. But the main thing here, which is where I would suggest the faculty, and also I tell the students, a lot of parents, students, and other professors, and even from the industry, people ask me, well, what should I study if generative AI is already auto-generating code, working together as several applications, creating a task similar to human, called agentic AI. Well, if agentic AI can do a full stack development, can already take over an IT administration, ticketed system, automate tasks intelligently, similar to human, why should I study computer science? Well, the main part is that that is one side, but we still need to be able then to create what would be the quality assurance and the responsible AI foundations for this, and also come up with the next level of development of mathematics, physics, as well as material engineering to create the computer for the future. Yeah, so this is pretty much at a very early stage. And here is where we need what would be the new experts. So that's why it would be also important to clarify and that everyone is understanding what are the synergies between quantum computing and AI. Um, a little bit, just a very short introduction on the current research trends. Alone, this would take me an hour if it was a full presentation. So I'm just only touching this for a couple of minutes in regards as to what is being doing. And the main point also about future scope and potential impact, about the areas that it can be gone in depth, and then they're definitely already well established and can be used them for growth. I'll do that presentation, and then at the end, I'm leaving 15 minutes, yeah, for everyone to be able then to ask me questions. So if you have any questions at any particular slide, please put them on the chat, and then I can answer them later, please. So that way we can continue with the flow. Unfortunately, I cannot stay longer than the 90 minutes that were already originally programmed because I have another, that would be then a meeting afterwards. But then, of course, if there's any lessons, if there is any questions on the lesson, please anyways keep them and then contact me later. So let's start with the foundations. In regards to generative AI, as its name says, number one, it was created using conventional computers. The main and most typical language in which it is programmed today, it is Python, using what would be then an IT environment. The most typical one is on the cloud and a so-called landing zone. A landing zone, think of it about a series, yeah, of computer servers that are remotely somewhere, and they have a so-called set of a stack software architecture. That means an OS system to assist on splitting off the hardware and virtual machines on small little virtual computers that can execute different tasks simultaneously, making them very, very fast. Right now we call them HPC, so highly powered computers. Then there's the next layer of communication between the applications and the hardware in a layer. Then there is, of course, then the area of access, or for what would be all the different services regarding electricity, heating, also the internal power control. Then there is more the application level close to us humans, in which you would have your typical database storage. You would have then what would be the area in which the main core of an algorithm will be executed together with the data in order to create a model. So which actually it's also trained, or already a trained model that is stored in one of these virtual machines and then be used concurrently with another piece of set of code in Python in order then to execute and generate some output. Could be text, could be video, could be an image, could be code, as already mentioned before. It could also be, for example, a particularly sound, yeah, be it a voice, be it music. But there are also different type of what would be then creations. There's different mathematics to this. For example, text is transform base, so predictive text, so bag of words on steroids. Then there is, of course, for the GANs, there are particularly autoencoders. So it is a set of neural deep learning layers that learn to look for patterns, and they would learn how to use and recognize these particularly pixelized patterns in order then to recognize something behind and then create something. So as for quantum computing, is a bit different. Quantum computing, I'm going to go this into much more detail because it's quite complex. But mostly what I'm going to start to say about this is, before I go into quantum computing, is that in the principles of generative AI, the focus is on basic algorithms already been set up, but mainly on the data. That means that they are trained with similar inputs. And so, for example, if I want to generate classical music, then it's trained on petabytes of data points of different classical musical songs, and then it would do a creation of a mix of this and then auto generate something that resembles the training output. So I could create, for example, in an VAT code and tell it, okay, auto generate me a song similar to Beethoven's Fifth Symphony, but give it a trace of pop and rock and salsa, and it would actually would do that with that prompt and create something similar to that, which is mixing and entangling data that was already being fed in. So it is not a true new output. Only from zero, so from nothing, the creativity can only humans do. And so only we can generate with our imagination something that has never existed before and then bring it on into occurrence. But generative AI application in this case would need to have that data in order then to be able to create something. And it wouldn't be, let's say, something that you can use immediately. Usually there are several iterations for improvement. So if you want to do photorealistic images or have a coherent picture of, let's say, a person, or even when you're giving it already movement, in order to reproduce these realistic and coherent outputs, you need to go to what would be then a coherence inference validation check. So that means that in the particularly output, you need to go on several rounds of prompting or a new data model. That means a lot of in the development, a lot of new data sets are given to already a pre-given module in order to make it smarter, in the sense that it will be able then to produce more coherent outputs. That means understand more. So the more data it knows, the better the output it will get if you prompt it to use that output in a certain form. So in summary, so generative AI advances content creation and simulation. For example, you can use those videos to recreate, for example, the city of New Delhi, just the city center or the airport of New Delhi. And you can completely, let's say, use that simulation to auto-generate, for example, people. If you want to do, for example, an emergency check, what would happen if there is a fire? How fast can people go? So you can simulate how many people can go through the exits, how fast are they going, if there's a collision, if there is a blockage, then how the police or the military can react to take people out. And you can do this all very, very realistically. And then again, use this also to automate and create other synthetic data that can be used, for example, for creating a safe management plan in regards to what would be then airport number of streaming of people or visitors. So this safety streaming package would be something useful out of that, would be a particular example. Now I'm going to jump into the more complex topic. Like I said, that was only an introduction to generative AI. This is not a lesson on generative AI, but more a lesson on quantum computing using what would be principles of generative AI. So that means that I would assume that you already have used generative AI on some point in time. Typically, everyone I speak about were in these type of lessons, at least they have some contact with Gemini, with Grok, or with Claude or ChatGPT. So I'm not going to go into that depth. I better want to change it into for you to understand what quantum computing is. If there is a need to go more into generative AI, I'm going to go that into a separate lesson. But I like to start here on quantum computing, which is an emerging technology in constant evolution. And it might not be something that is present for you every day because not everyone has one. So there's not that many in the world, but it's going to impact the world tremendously. And the amount and the size of quantum computers today, they are improving and creating an immense, what would be then, evolution jump, from 1 year to the next, or from one cycle, from one generation to the next, and that's about, I'd rather say, 10 times faster than a common computer. So think, in 1920, Paul Benioff started a Turing machine. And in 1982, Richard Feynman started simulating physics, so quantum physics, with classical computers. But it took good almost then 30 years for the first quantum computer to be made. Why? Because there were not enough materials. Quantum computers need to be on absolute zero or close to absolute zero. So that's 0 Kelvin. In order then to be able to stabilize what would be the stimuli of light, so the little tiny photons. And here the first commercial quantum computing was done at D-Wave. And then 6 years later, so as you see here, the gap in the evolution starting to get smaller. IBM created the first quantum computing that can be accessed through the cloud. And 3 years later, Google started with the same trend in Google providing then quantum supremacy. And now in 2025, there is already a set of over 17 different providers of quantum computer access over the clouds. And now that new emerging tech is that of QI, and so quantum artificial intelligence. One example of its use is on life sciences and health for molecular modeling, in which if you look at a particular model, also chemical model, all or for example a virus or a cell which have got DNA. The DNA is very close to code in which it can be sequenced. It can also they're all data points, and here is where we're using generative AI to create what would be different permutations of, for example, a medicinal treatment or a vaccine treatment with a dose with a particularly chemical model, and then simulate how they react, including that for a particularly set of DNA code. So this allows for personalized medicine for the very first time. Why? Because, for example, sequencing, for example, an entire village, of 100,000 people in a conventional computer would take about 1,000 years, and a quantum computer would just take a couple of hours. So that is one of, let's say, the new type of aspects. Now we can see here. So to deep dive a little bit more, so the way that it works, it uses the concept of quantum mechanics, which is a subdiscipline of physics, to process the data. That means the quantum state, so both photons have the same state at the same time. Regular computer uses bits. That means a flow of electricity or no flow of electricity. So that means that a bit can only have one particular state, also in memory. And a quantum computer both photons have exactly the same state while they're doing a calculation, and when it stops, they collapse, and only one state finishes the calculation, and that's the one that gets measured. And this particularly collapsed state is what we call a qubit. And it allows us to do calculations at, like I said, a rate that is exponentially faster than conventional computers. And just a little summary on how they work. This is your typical remote cloud server. And so they use binary bits, so classical theory. They're used for daily processing of data and calculations, and they're always sequential. That means if you would look at hardware in your software, you will see that in what would be an ASIC application, the calculations would be on the task and the clock monitor done one sequence to the next. And that's where we have then multiple cores in order then for it to appear that they're semi-sequential or almost immediate. Yeah, through the years, they have low error rates, and they can be kept at room temperature. For example, your mobile phone, the computer you use, your laptop, and information here is subjected to the classical law of physics. So if we look at a quantum computer, here you can see the one that we have there in Switzerland. This is not your typical quantum computer. Is a pretty powerful machine. So a person would be around this size. Here's where we have what would be the entire photon collider. And here's where everything is kept under sub-zero. And these are all the measuring points, to measure what would be then the last state. Then we have a secondary layer. In this secondary layer, we do the quality assurance of the particularly first calculation state. So one disadvantage of quantum computers is that even though they're used for fast and complex calculations, and they can parallel integrate sets of data, and they use probabilistic calculations too, but they have these high error rates, which need to be kept ultra code. So in order to first avoid any error rate, the entire machine gets checked to ensure that the material is not damaged, there's no micro fissures, there is what would be then a particular temperature state. So all the sensors are checked, and then there is the first observation that is done, and then the first calculation. And that is directly checked on what would be the emulation layer. So the layer, the application layer, I'm going to go through this in a separate slide more, in which we would know if the particularly measured state was measured correctly, yes or no. And then there is a simulation of a quantum computer using high-powered computers, which are 4 running in parallel, simulating, let's say, having both states as a qubit would do. And they would also answer and calculate exactly the same task. And then both would be then compared. And if the answer keeps being right, then the quantum computer gets what would be then a reliability index. And that's how we would know that the particularly output is correct. And those are the ones we can sort out and later on use for different applications. And what are those use cases? Well, artificial intelligence, as already mentioned, generative AI, on machine learning, and particularly then on blockchain for cybersecurity. So on this part, again, on the summary, so quantum computers use qubits, which are the fundamental units of a quantum computer, and they enable states beyond classical bits. They use what it's called in quantum entanglement advantage. That means that it links both qubits to enable a complex problem. I mean, they're working together as if they were a team. And they also use a principle in physics called the superposition principle, which it allows the qubits to represent multiple states simultaneously. So in that case, then they have both states at the same time, increasing the computational power. And this is just very, very basically explained. To go into this, I would have to be a physics lecture, which I'm not going into here. So I want to stay more into a higher level for this hardware part. And here is the picture that I promised you in order to give more light. Yeah, so as you saw at the very, very lower layer, the hardwares where we have the topological qubits. Yeah, so it's the quantum plane. We have then what would be the assurance, that this is, let's say, the measurements are running correctly. So one of them is checking the cryogenic control and also the room temperature control. So in this case, this quantum classical interface is the one that gets first validated. Then it has got an interface to an emulation. And so that means a direct access control, in which is these high power computers, in which here is where we have on top the solutions and the software and applications and agree just like any other computer. And here's where it also runs that validation layer. So in up to the hardware layer is where we have analog signals. And then on the connection to the emulation and the simulation layer is where we would have our high-speed digital based on the HPC connection. So the way that it would run would be that there would be then a particular task is running up and down, and then there would be again the measurement, and again the particularly validation step then at the solution level. So to jump down a little bit more, so the way that it works is that the quantum processor, the one that is in the cryo chain and the control electronics, as well as the calibration and control framework, these are all on their absolute, they're all on their near absolute zero. Yeah, here is where you would have then what would be the hardware near control. So where you have connectors, cables, filtering with a sample amount. And here's where you have your QPU and a lot of parametric amplifiers in order then to measure what would be the last state of collapse of the qubits, as well as where the areas then in which the chip system is. There's still quite a need of research here in chip design. And here is where we have then what would be the validation level, in which what we do is electrostatic simulation. And we also do what is called a Hamiltonian simulation, that the one that I mentioned, that it just simply checks if the probabilistical state that was measured was actually then the right one, because it gets validated with the higher level, in which this particularly circuit simulator does exactly the same task as the level below. And they're both then checked to see if then the output is correct. So this was 2 plus 2 came 4, these ones 2 plus 2 came 4, and then they will give more and more complex, what would be then tasks, and then the higher the amount of correct responses, then the higher the amount of what would be then characterization and reliability. So from this level is the jump from analog to digital. And here's when we come here into the calibration and control into the HPC, the power computer, where we have the control software, in which we're doing then the particularly characterization, so the validation. And here is the level in which we are already measuring them and checking that everything's in order, or there would be then a change. What's what we call in a calibration. So it's the quantum verification validation layer. And here's where we have the pulse trajectory simulator. So it's what would be, think about a beam of light gets sent up, and those low temperature levels, it can be stabilized for a particularly needed of time in order to set up and give it a particularly task. So that is what we're doing here in this simulation, which is the one that is also checking not just the algorithm, but also the measurement check. So then we have our very, very typical a compiler and languages, but their quantum languages are a bit different than conventional computers. And then we have a quantum algorithm, so our PQCs, as we call them. And in this area is where we start already profiting from applications. So just like you would do in a conventional computer, using, for example, a really high computational source, similar as you could be using a TPU over Google Cloud. Here's where you would have access to the PQU, as we call it, over the um, application emulation layer, not a simulation as on the cloud. Yeah, so that's for what we did, for what you need in order then to access. And so it's a product demonstration platform, which is what we have here. So you would never have a direct access to the quantum computer. You don't want to. It's very costly. And it takes a lot of resources to do this, a lot of money to do this. But the areas that you would have access more is over the cloud on the particularly dark layers. Yeah, so the device development, so on this area, as well as in the algorithm development platform, and into the what would be um, application layer. Yeah, so the commercially viable quantum computer, though that is one I'm going to jump a little bit more into the next slide. Yeah, so just going here, very, very, very generic. Like I said, this is just an introduction. It's actually more complex than this. So let's give a look at the most simple quantum computer. Yeah, so you would have here, yeah, this is a very small computer that you already can find in India. It has got and it's around 470 million USD dollars. Just that you know, it's not something that everyone has. Only certain research centers, and this small one is just 472 million. You can imagine how much it costs what we have in our research center in Switzerland. So here you have this very, very small quantum processor, which is integrated with the amplifiers, the ones that I mentioned before. And then there is the attenuators, so like sensors that are used in order then to do the stimuli and the measurement of the photons. And this is the administration and the check of the robust cryogenic control system. And on this side is where we will have then the management of the verification of the electronics, what we call the QPAI sense. This is scalable control that reads out all the electronics from all the layer stack. So this is what you would find from the previous slide. And then there is a connection to the application layer then from here. So what are the differences and similarities? Well, when you start using generative AI on your classical computer and algorithm, of course it solves the problems, it does that. But when you jump in using generative AI on a quantum computer, and using qubits, you're going to see that the information processing is going to be different in the sense that number one is immediate. Yeah, so if I make a video on VO3 for 8 seconds, it takes 10 minutes to generate it. It doesn't actually follow everything I want. It's not 100% photorealistic, and it just simply takes too long. Yeah? And if I were doing that, the same type particular task in a quantum computer, I could make an entire video of an hour, photorealistic, just with same texture, cinematic level, as if it was done an entire computer, an entire Hollywood film from 2 hours in less than a second. Yeah, so it's immediate. So that means that it has this complementary strength. Yeah. So through the problem-solving methods that it has, that it uses the quantum computing mechanic approaches and its mechanisms, but like I said, through the application layer, through a conventional computer, high-power computer application layer, we're able to give it normal tasks, which is able to execute very fast. So it is viable, so why not use it? Because again, it's still quite costly. Nevertheless, we can see where in the research area, but in the research, let's say, applications of learning, what can be done today. So there's synergies. Yes, of course, your university is not going to be buying one this day or the next 10 to 15 years, but you can have access to them over the cloud for still what would be an affordable amount. Yeah, so less than $2,000 for the use of 500 qubits, for example, for students using around $18 per what would be then course term, just when they would be using then the direct application. So still, like I said, you cannot do very powerful things, and that's a good thing. It's just simply would be enough in order then to learn the sense of the algorithm logic and the potentials of using the synergy of quantum computing and artificial intelligence. So what is one of the synergy? Yeah, through this parallelism, yeah, you can have different multiple states. That means that how can that computer generate, like I said, an entire 2-hour film within a second? It's because it's all the qubits are running in parallel with the different type of tasks. And so one is generating the scenery, one is generating the sound, the other one is generating the textures, the other one is generating the story, the other one is then taking care of the movement. So all of these are different set of algorithms that they entangle themselves and they get distributed along the qubits. Yeah? And then there's, of course, on the application layer, the machine learning algorithm. But there is also an improvement iteration going on there in order then to see that the performance is matching the requirements, and it's also handling complexity. So it's all these models talking to each other. So we know that from agentic AI that can happen, and they are the ones who have to take care of the solution. Yeah, so they are the ones that then in the end bring out the output. So when we move now into quantum machine learning models, yeah, they of course support vector machines, but they're using the variational quantum circuits. And here, because they're running, like I said, all at the same time, yeah, they are incredible in speed in regards to classical models, and also it would be the accuracy. So what you can do now here, as I mentioned, you can simulate to better understand behaviors and properties. You can use it to optimize different experimental setups and improve the precision efficiency. And very, very important, also use it to improve the quantum circuits themselves, improve the quantum computer design itself. And so what are the areas that we can do? What are the materials that we can use in order to reduce the size, bring what would be a more stability, a higher reliability rate, and reduce what would be then the amount of power, and bringing about here also a new type of physicists that, of course, are multidisciplinary, that are also, of course, AI experts or quantum experts, material engineering experts, in order then to bring what would be a much more stable environment to reduce the size, but keep the same performance. So through the challenges, of course, yeah, is the hardware limitation that I already mentioned. Yeah, they're pretty big. They're quite complex. They require a lot of maintenance. They have error rates, and there needs to be still first a qubit coherence validation, which impacts the integration with what would be then a normal application layer. And creating a quantum machine learning algorithm is quite complex, and so we can do that in a separate lesson. In which I can show you how it is done, the differences. But the overcoming this complexity in the algorithm for processing, it's important, and to reduce the noise reduction. So there are ways on the mathematical evolution how to do this. But nevertheless, yeah, so this is an emerging tech. So it's a revolutionizing technology, but it would allow you to enhance any AI capability you can imagine. And then, of course, enhance itself. Yeah, so you can help bring the next evolution of quantum technologies. So what we can do then today in the research, and at the same time what students can learn with quantum computer and AI. Well, as what we're doing right now is this breakthrough machine learning. So we're have the results and recent experiments that have demonstrated this advantage in that it has done and learned tasks beyond any classical methods. For example, a generative AI model takes good 3 months to be created and trained. If you were doing exactly the same thing about creating ChatGPT 5, yeah, and it took OpenAI a good couple of years to create it. If it had been done in a quantum computer, it would have just taken simply a couple of weeks. So it has the ability to enhance data and create simulation data that would have been impossible to do before, because it would have taken thousands of years in order to create all those permutations. Because it has this what would be then tremendous data generation and simulation capability. And at the same time, the algorithms, the validations that we're doing in the emulation and in the simulation allows us then directly to check for effectiveness immediately. And because of this tremendous boost that you have and of power, and of course, it's um, for example, you have the ability to do a lot more complex problems. So there are global research partnerships. So there's different research institutions worldwide that we're cooperating. There's the World Quantum Congress. It runs in Chicago once a year, which we share different knowledge and resources. There's also research and collaborations in system development. As I mentioned, there's still a need to reduce the size and also bring what would be more stable materials to reduce the error rate for demonstrating practical applications and other type of use cases. And there has already started the last couple of years, an open innovation network to collaborate and foster on this discovery and application, and mainly then on a peaceful way. So now we come into the meat. Yeah, so I made you a little bit hungry, and now let's eat, as I said sometimes to my other students. So how can you have a direct access? Yeah, so we could do that in a separate lesson in which I'll walk you through Google Circ. There's other ones, like IBM Quantum Experience, but Google Circ actually is a very what would be affordable in quotation marks, because it's still very expensive, but it still allows an accessible environment for experimenting and learning quantum algorithms and its use. There is a set of open source libraries that can be used in integration with AI models and enable rapid development, quantum research with Google Circ. So these are the ones I will be mentioning in our next lesson. So what is a future scope and potential impact? So as you can imagine, we are now moving in what would be the next or closer to the next singularity. So a lot of people still are of the belief that we're closer to traditional general intelligence than we were before. Well, in my opinion, we're just what would be then Kerosene, yeah, getting there, but not there. So we don't have artificial general intelligence. What we have is a narrow AI that's able to do very high and cognitive complex tasks and probabilistic decisions similar to human being. For example, an autonomous driving car from Waymo knows the road, understands how to read traffic signs, understand when there's a person, when there's a cat, when there's a bull, how it should react if a car wants to change lane, but it doesn't turn the blinker, but it's still able then to do that probabilistical check and reaction just like a human would do. So that means it drives and knows, for example, the city of San Francisco in every single corner. And it was trained in a simulation environment to do this, but it took good 6 to 7 years for that to happen. Then the same thing would be, like I said, already mentioned, with the use case of precision medicine. It takes years to be able to develop and create what would be then a medicine for a certain group. And unfortunately, that medicine is developed mainly using male in vivo test subjects. So you have the entire female population and also elderly and of course young human beings that are out of those in vivo tests for ethical reasons or for non-availability. So these medicines have that data bias already built into itself. But what about if we could use then all their DNA samples? That means they don't come in contact with what would be maybe a potential dangerous chemical source. And then we would be using a quantum emulator in order then to multiply what would be all the possibilities that can happen in their genome by taking different types of doses of that medicine if they had that particular what would be disease. So without them ever coming in contact and then ensuring that it's the right amount or if it's adequate. And that within hours. Yeah, so simulations that would take 80, 50, 100 years to be done, like I said, just simply in an almost immediate effect. So their advantage is that it can just simply do immediately this high complex and high dimensional data distribution sufficiency. Imagine it took good 2 years to jump from language models, just simply predictive text, into multi-model models like ChatGPT-5 that can generate images. It can, of course, create and have mathematically reasoning. It can also be able to learn to have what would be a basic rationality and inference model. So they are all combined. So if you were using, for example, the same amount of data, you can web scrap everything and create what would be an immense, gigantic, what would be then advanced AI. That then you can use for creativity. So models that would be able to do problem solving and designing novel solutions beyond any capability. Some and this is already accepted in science. Some of the last prize Nobel Prize winners on AI, they said or they use AI in order to make a simulation. So imagine the power of using a quantum computer for all the mathematical and physical and as well as what would be then social problems that we have today. Big question mark. That could be resolved here in this area. So, but it's still the challenge then of the quality assurance of these. We still need to use it for optimization of these simulations. And here is where, like, again, on this quality assurance layer, there is a lot of research work that can be done. So what is then the predicted transformations in healthcare? Yeah, so for drug discovery, personalized medicine, as I mentioned before, and new treatment strategies, financial risk analysis, they can assess and check for faster data processing. For example, protect increase and create encryptions that are almost impossible to decrypt. At the same time, be able then to recognize probabilities. For example, if doing an investment that a company might go bankrupt, if it goes bankrupt, that recuperates. Do a very precise prediction of crashes or what would be then reliability of companies in regards to, for example, their management. We can do material science advances, as I mentioned. we need a lot of work here on novel material design and simulating this different complex molecular structures efficiency. So the future of a new jobs come into, like I said, multidiscipline person. So someone that first starts studying computer science, and it learns then material science, and then it learns physics, and then it learns, of course, then what would be advanced quantum computing. And by having this multidisciplinary knowledge is able then to create what would be the materials for the quantum computers of the future or for other applications. And then, of course, cybersecurity enhancement. And so the quantum AI enables a secure communication and advanced threat detection like never before. But the cybersecurity part of this is a different lesson all on its own. So where I like now here then to jump in is that there is no y-axis, and that's actually a good thing. And so that, and also the possibilities of what you can do in the cloud are also been by design limited, and that's a good thing. Why? Because there's ethical consideration, societal and practical considerations of what it can be done. So one of them, one moment, sorry. It's that if everyone would have access to the core emulation, yeah, they would be able then to, let's say, reverse engineer and crack the code of a crypto wallet, for example. So this is a tremendous ethical concern on data practice, privacy, and algorithm BS. So it has to be addressed carefully. So it could also create what would be if it's used negatively. Yeah? So it could directly create a new series of scams. Yeah, so that's why it has to be thoughtful consideration of the consequence, and that's why not many people have access to a true quantum emulation. What you would have access is to a quantum simulation over the cloud for responsible development. That means that you would be able to use the benefits and be able then to learn to create what would be the basic algorithms. Still are very powerful, but they would not be that powerful as to, for example, cracking a crypto key, for example, password. But you could still be able then to create a solution for example, healthcare assessment of, for example, a new chemical composition to material, and do that simulation quite fast. And why is that good? Yeah, so because there is then the agreement that there needs to be standards, regulations, and laws. Yeah, when anything or anyone is using AI, and I know I use the word anything. Why? Because there's also AI talking to AI and generating AIs, yeah, agentic AI. And this have to be built using responsible AI principles. Here I'm using the source of Microsoft. And what is responsible AI? Well, responsible AI ensures that any AI application is done using ethical and responsible AI practices. And you would say, well, whose ethics? Well, we agreed on the Responsible AI UI Act, as well as the NIST Act and other AI guidelines, regulations, and laws on the UN Charter. Yeah, so on what would be then human rights. So this cannot be done in isolation. Yeah, so there are other principles, and that is, for example, fairness. You cannot use an AI or an HR to discriminate the CV of a lady versus a man. They got to be sustainable. That means that computers and the way that they are powered need to be using a green source of power, like what would be then solar power or water power, for example. Data privacy, ensuring that the digital rights of all the data owners and data users, is given. Accountability, that means the company or the persons responsible for the AI have to ensure that they are bring into responsibility, into accountability if something goes wrong, and it has to be explainable, transparent, How was this created? How was this particularly system application created? And then for that, there is the AI lifecycle. And so it is a set of principles. That means it's a process check. Yeah, the requirements have to be developed, mapped to an architecture, then map in a diagram to all the components from the functional architecture to technical architecture to the software module to the data that's being used to the team that's doing it to the test cases to prove it and the test case results, the verification test cases against the requirements and the validation to the expectations of the end user and the client. And all the data has to be checked from source and usability. And it has to be audited, checked, and qualified by a particular responsible AI expert and a quality management expert. And always in reporting to management and to everyone, it has to be in control of the results. And that is what we call an actionable governance framework. And then here is, for example, also where the client, the user, is identified. And there has to be an auditor to make an assessment, a risk assessment, to learn from the beginning what could be the risks of that application. So if I would be using that CVS scan assessment tool, yeah, it would, let's say, create a lawsuit if that would be happening, for example, in Germany, yeah, or here in Switzerland, which is not allowed to discriminate based on age, sex, gender, etc. So this unintended risk, they have to be analyzed. So there is, for example, like a mind map of all the different sources that what could be done. So how to eliminate that. And then there would be a filtering that would take care of the picture, the age, the gender of the person, and just simply leave the experience and capabilities, and then make an assessment versus the JD. That way, the pre-selection process would be unbiased, as an example. So these risks then associated with that implementation were already then taken into consideration while designing the AI system. So as this must be controlled worldwide, and there's this governance shift that started in 24, will continue till 2027, till all countries that have agreed to this by design have what would be either a guideline, a law, or a regulation if they want to operate and create AI applications within that area. So in the EU, we have the EU AICTE, how to do things. There's already a training data summary template this year. Then there is internationally the OECD that's created the AI principles for safety and privacy. In the UK, there is the IC evaluations, which is a playbook on how to create an AI risk assessment, independent on how the AI was created, if it was a classical computer or quantum computer. And Singapore is even farther out in that they have completely created a model framework just for generative AI evaluations. And why is this important? Why I put it here? Because a lot of the generative AI data and algorithm, so the models, are very, very black box. But you still are responsible for what's happening if you are the manager, the owner of that company, into what happens when you use that application in the field, or when you already industrialize it and sell it, either as a service or completely the application is a solution to a client. So there has to be then at first what would be a law assessment and a technical assessment to check if it's fulfilling compliance. So in conclusion, yeah, so generative AI and quantum computing, yeah, can bring in about new frontiers. Yeah, there is a lot that we have to do here. Still a lot of research that needs to be done. And there are a lot of potentials, yeah, to transform current technologies. And very, very important is to ensure that this happen with responsible innovation. That means that these computer powered, these technologies have to be ensured and controlled that they don't get misused, yeah, for criminal purposes. But it's done with ethical approaches, which are essential for the future of artificial intelligence. So that's it from my side. Yeah, so if you have any questions, now it's the time. I'll take the questions. I have quite enough time now. And you're very welcome to contact me if you have any questions afterwards and we're not able then to go through today. So do we have questions on the chat? Hello? Yes, Sonal? Sonal? You raise your hand or?
Yeah, technical team, please allow Sonal to raise the question. Abhilash, Deepak, Dharmendra, are you all here listening? Please unmute the participant.
Hello.
Yeah. You're audible.
Yes, ma'am. Thank you, ma'am. Participants, do you have any questions so that we can take up? Yes, ma'am.
Sonal Pawar had a
Sonal,
question.
yes,
Sonal.
Sonal had raised her hand. Deepak, please
Yes, ma'am.
unmute her.
I did, ma'am. Sonal Pawar, I did. Sonal, ma'am.
No, she's not. She's still muted.
Sonal, ma'am.
Sir, actually, I am getting to post thank you, but
Okay.
by mistake it raised and
Okay. Smita
Okay,
Borkar,
no
ma'am.
problem. Okay, I see one question in the chat. Smita.
Smita Borkar.
What are the areas in which research is possible for quantum computing and cybersecurity? A very, very good question. And very, let's say it would take me another lesson. Like I said, this was the first introductory lesson of this series. Well, actually in anything. Yeah. So on from blockchain encryption to what would be any type of encryption, any kind of method. So it's actually quite broad. One of the areas is on what would be creating new novel ways of protection. Yeah, because with a quantum computer, you can crack already what would be the standard cybersecurity weaknesses that exist on conventional computers today. So that's why it's good that not everybody has access to that kind of level or emulation, and it's still very, very, very costly. But then nevertheless there are so criminal sources that might want or might have, which is coming into what would be a speculation layer. So in order to prevent what would be a cybersecurity attack, you can use on a quantum computer, for example, a simulation of a quantum attack. Yeah. And for this, for example, there's already NIST frameworks, or also from INISTA and NISA. And the Talus Group, they published the 2025 Data Threat Report, in which they are able then to, let's say, bring about the risks of quantum cryptography risks. And also in this case, for example, like NIST addresses that there's a threat break of the current encryption. So they have developed new standards. It's called post-quantum cryptography. And they include new algorithms, like FIPS 203, 204, which were released a couple of years ago. And they have now provided very good standards. So in order to what would be to warn if there's an encryption breaking for quantum computers. And this could allow organizations for which this is critical, like banks, or the government itself. You don't want, or wherever your data is kept. You don't want anyone maliciously breaking into what would be the medical system in India, for example. They also need money. They also have accounts to manage health systems, healthcare, and posing a risk. Why? Because if you would be using what would be FIPS 203 or 204 as a criminal, you can already break the encryption as RSA and ECC. Yeah, so they become automatically obsolete. So what you want is then now to research on, okay, how to avoid this threat. And there's a huge, I think the next 5 to 10 years, there's going to be a huge rise of experts are going to be needed. Yeah, people that want to learn that, how to protect individuals, organizations, nations, to protect their sensitive data. And of course, this accelerated vulnerability that is coming is definitely going to be very, very high. So, and if you're interested in studying that, I would always suggest that once you finish in computer science, you go into mathematics, and we need the mathematicians. Why? Because we need people that are able to create a new algorithm development. Yeah, so it takes at least alone 8 years to develop them. Yeah, so and to create something that's resistant against quantum attacks. Yeah, so it's very, very, let's say, complex. But there is a huge, I think, potential on this. And
yes.
you will be doing something very positive. Okay, so next question from Smita. Can you give me a starting point to start with, like any algorithm like Shor's to just begin with? Yes, we're going to do that in the next lesson. Yeah, so not this one. This one just simply to introduce you, to first give you that first shock. Yeah, and I didn't want to go too early into that. So in the next one, yeah, we're going to go more into how, let's say, the particularly hardware software new layer works, like Shor algorithms, and first understands the mathematics and the physics of that before we start, for example, then with QCIT, for example, or with Quirk. So and once we jumped into that level, then we can jump into let's say the AI application of that. So we can do a small application in this.
There is another question. Harmanpreet Kaur, what kind of post-quantum algorithms can be used for cybersecurity?
Yeah, I already mentioned them. I already mentioned some. Yeah, like the set already created by NIST. Yeah, so the FIPS area, like for all the PQC standards. So there is also the MLChem, MLDSA, SHLDSA, which are quite complex, and it can only run on what would be a quantum computer with at least 2,000 qubits. Yeah, so if the one that I show you, that small one, has around 240 still, so it would not run on those. Yeah, and there are a lot more. Yeah, but that would take me quite a lot longer of a time to go through them. But let's say that if you just Google Cracktl Kybernist or post-quantum cryptography algorithms, you're going to find, for example, from Archive or from what would be then other journals, a lot of what would be then papers on NIST quantum cryptography. So, or for example, assessing benefits and the risks of quantum computers. There are what would be new ones that they're being raised every day, but they have not been, let's say, assessed and trained to be able to, let's say, detect, to know if it's really a quantum cryptography would be then attack. So that means to recognize them. But there's the ones, I think maybe your questions in regards to on let's say encoding. Yeah, so what would be then quantum encoder? I mean, you could use FIPS. Yeah. But that would be a pretty good mathematical lesson. I think that's a good point. I should add it for the next lesson that we go into to mathematics. But first, you would need to understand what are the basics, for example, how a public key works, yes, in cryptography. So that then we can go and then understand how the quantum key distribution works. And so to offer this secure exchange. But I mean, there's already the Shor's algorithm that was mentioned here that does all these factoring, all these large numbers, which is the mathematical foundation. But there's another one that it works also, but it's a similar way, which is Grover's. Yeah, so Grover's provides a quadratic speed up. Yeah, so it's like a brute force search, but with gigantic steroids. And so it weakens symmetric encryption and is able then to weaken hash functions, and it just halves their bit level security. So it's a nightmare. But like I said, you need very, very powerful emulations to be able then to do this, and not everyone has access to those. But yes, we'll go into Shor's and Grover's algorithm next time, into the next lesson. The quantum decoherence complex concept. That is very, very good. Very good question. Well, as I already mentioned in the slide, there is a need to check how reliable the measurement is. Yeah, so when there is the collapse, yeah, so that the photons are just like blinking, and then let's say the stimulation stops, yeah, and then they just simply stop at one state, this collapse. So what happens is that then there is the loss of the information that happens then. So one would say that through the loss of this data, yeah, the system loses in a way then the behavior, and it's called simply the coherence. So when they're both being stimulated, yeah, when they're both connected, yeah, which is called this superposition and entanglement. And maybe also after mathematics we can also go into the physics of this. But there is, let's say, after the stop of the simulation, yeah, and there is a collapse. There is in between this, let's say, and before you do the measurement, that's why you have to wait till the collapse has finished. There could be a noise that's happening. Yeah? So they're very, very, very sensitive. They're very, let's say, what would be? I mean, they're not robust, yeah, for a better word. So this fragile quantum state, you know, on the computation, yeah, it is, let's say, it turns the quantum information into the classical information. Yeah, but when the collapse when the measurement of the collapse happens before the noise stops, yes, before the final state comes, that's what could lead to the error. Yeah, so the coherence, in short, is the fundamental challenge in building the stable, yeah, reliable computers. Yeah, so you need is the way or that you need to create then a reliable measurement or strategy to just isolate the qubits from their environment and ensure that they keep that state, their double state of coherence. I mean, this is 1, this is 1, this is 0, 0, 0 for the longer period, and then you know when they collapse, and then they keep again their last state. So I hope I was able to answer the question. Okay, so how does the scale of government-funded quantum research in countries like USA, China, and European Union compare to that what is India and Brazil? Well, very, very good question, but actually India is again got what would be last 5 years 10 $10 billion US research investment fund. So India is investing massively in this. Yeah, so it's scarily compared to what we're investing in the European Union. I mean, of course, USA and China too. Yeah, but Brazil, definitely not. I mean, Brazil is a very basics, very basic investment, but India is even higher at the part or equal than to the investment of China, which is gigantic. So you have a huge potential right there. And then with the rise of quantum computing, do you see quantum computers as a bigger risk for creating zero-day attacks or as a bigger opportunity to defend against them? Both. As I already explained why, both. So that's why companies need to create what would be a quantum computer to risk assessment governance. Yeah, and that's why if they have a responsible AI governance, that would allow them to create the risk assessment to build in what would be the new address mechanisms for the protection. But then, of course, there's going to be malicious people. So you need to find out. That's why FISP was created by NIST in order to recognize the attacks. So you're going to be needing in the future, yeah, they're going to be JDs of ethical quantum computer hacker and ethical what would be then PQC algorithm developer. So those are new jobs that are going to happen. So that's why I told my students, don't worry about generative AI and is AI creating code. No. The emergent tech is going to create a complete new set of let's say new needed jobs, particularly on the cybersecurity sector due to these zero-day attacks. Yes, India is funding through National Quantum Mission, correct? Oh, and how does the future look like in AI and quantum computing? So you want me to have here my crystal ball? Well, I have a crystal glass. But yes, so the number one thing that's going to happen is that the level of access that we're going to be having, and I think that I hope that happens. But number one, HPCs are going to become cheaper and cheaper and cheaper. So let's say what an NVIDIA HPC core costs like $5,000 would be getting reduced to like $50, and we could have it in wearables. We're not going to be needing computers to work like this. So maybe there would be much more advanced quantum computers, and then we would be able then to have true AR, VR at work or at home, and then you can use a complete, let's say, interactive simulation like a metaverse. Yeah, that it doesn't run because HPCs are very let's say slow for that. But if let's say you would put the metaverse into quantum, yeah, that could make complete realistic things like right now I'm in the office that you can let's say completely bring the presence of everyone there. It can create new levels of collaboration that would allow let's say hybrid work even, let's say, to be only relevant for certain things. You can it will change the entire setting of the industry, of the cybersecurity, the life science industry, the banking industry, as well as what would be the data engineering industry. Why? Because the future that I see is that because a lot of models of generative AI and AI have been trained with data that nobody knows where it comes from. That's why I say don't be afraid. Oh, well, I'm out of my data engineering job. No, what we need now is the rise of the vibe coding expert fixer. Because the vibe coding generative AI application didn't do that good of a job on ensuring that is productionized and can be used for like a bank or a hospital. I mean, you can't. You need to use responsible AI principles. So you're going to need as software quality assurance responsible AI expert to fix all the bugs that the AI created or the incompliances. So that's going to create that. Or the data that the model shouldn't have needs to be deleted. So it's called pruning. So don't worry about data engineers. So if you want to be a data engineer, you still should be a good data engineer. And there's going to be a new job role, the data pruner out of models. So just simply getting data that shouldn't be there anymore out of that and creating more specialized models. So a bit smaller, yeah, but that they're, let's say, more task focused, but also with the ability to sync with bigger models. So there's going to be the let's say model interface management creator, application manager. So that's going to be a new set of roles. So it's going to be moving into doing what I like to call all the quality assurance that an AI still cannot do right now. It's because it's not there. And that's, I say, 5-10 years till quantum computers become much more commercially viable for, and there is also a better way of regulation and control of this. And then on healthcare is tremendous. I mean, Novartis, which is a Swiss Indian company, is already using it right now. Yeah, so there are a lot of use cases on this, and that means a lot of damage can be avoided from this. Yeah, so if you're doing an in vivo simulation and no longer on people, like I said, bringing personalized medicine, personalized treatment, and on finance, it's I would need another half an hour to talk about that one. I want to take another question. Someone's AG is raising. Ashish, you're raising your hand.
Ashish, sir, you can ask your question. You're unmuted. Ashish, sir. Ashish, sir.
Yes. I'm just wanted to know the utility of quantum technologies specifically to healthcare and finance sector.
Yeah, I mean, I already mentioned, but to finance, I already give you some use cases that of cybersecurity, protection, data management, and what would be then for all anomalous detection. And so how do you detect if someone's telling you the truth while you're making an investment? Yeah, so a lot of companies, out of fear of getting devaluated, or a lot of startup unicorns, sometimes they live from the stories that they tell before they gain an angel investor. So some companies are using, for example, you can create a model, yeah, and give it all the data to analyze people's voices and sentiment, and say, oh, well, is that person telling the truth? He's telling me his startup is amazing, is great. Shall I give him the money? So then you can create that application, and then it will tell you very, very precisely if that person is telling you the truth, yes or no. It's a bit scary, but for the investor, it's a very, very useful application. Yeah, so and imagine that, and you have that in your wearable. You have that in your glasses. So you can sit in a meeting. You're an investor, and there's this, let's say, people say yes, invest in my company, and it gets immediately an assessment if that person is telling the truth, yes or no. So that, or it can also be used, for example, a probability when looking at statements of a company. Yeah, and there is another company looking for a merger. And so banks also do a lot of B2B, and that is when most of their money is made, they can decide to do the merger or not, because then they can analyze all this data immediately at one point in time. That is not always, let's say, possible, and then they're able to see, well, doesn't make sense. This company has a probability of getting bankrupt in the next 2 years, so no merger. So that kind of way. So you can do things that before would have taken years and speculation, and do it very, very mathematically, let's say, precise. Yeah, and from data taken out of what would be then particularly sources from web scraping the internet, which companies with the same, you can create a situational analysis. That merger occurred, this were the errors that happened, this company in this particular economical situation got bankrupt, those were all the other, let's say, N+M influencing factors, and you can put that all into a big, huge mathematical equation, and then have it simulate and then give you a result. So the applications in the finance research is there. I can go on and on. There's so many, and also very, very interesting.
Thank you.
Thanks for your question.
Yeah, and context to healthcare industry, healthcare sector as such, how quantum
that's
can
what I
be
mentioned.
used? Utility of
Yeah,
quantum in healthcare.
Sorry.
Utility of this quantum technology. Utility of this quantum technology with specific case in case of healthcare.
Yes, we'll do that we'll go into detail into the next lesson for that. But as I mentioned already, precise treatments. Yeah, treatment. Imagine just to you. Yeah, so you can use a quantum healthcare to create an ashish pill if you have a headache without any side effects. Yeah, or what would be the right vaccine for you, or the right, let's say, treatment for your mom. So it's personalized healthcare, which would have been impossible before. And of course, avoiding any side effects. So that is one
So,
of the
ma'am,
most
it,
incredible newer applications. It's on
so
research right now.
it would be more precise and affordable too. That does it mean that?
Yes, excellent. That you should tell to the healthcare companies. But yes, I think in that case, then we're coming into the ethical part, the responsible AI, very, very well put, that then the governments would need then to, let's say, bring into that. Yeah, so create affordable healthcare so that there's right now already two classes of medicines. There's the generic medicine, and then there's the big medicine. If you go to a pharmacy, you can tell them, well, give me the cheap ibuprofen or give me the ibuprofen from Pfizer. Yeah, so you can choose. And so it's in a way there, but yes, it could bring it more affordable. But because they're investing heavy money on this, there has to be, let's say, also the governance framework, yeah, so that the government decides, well, for who it makes sense that they get that access. And then here we come up into the fairness, yeah, that you say, okay, well, low income families, they would have access to this type of medicine and treatment. But then you come, okay, and if you're earning more, then you would have, let's say, to pay more. So if is it the same? Is it right, or is it wrong? Yeah, that they're paying less than you. Well, shouldn't be the same price for everybody. So you would then need to come up that yes, it can do it. But then here is where, and a very good point, we need also those roles in the government, in companies, of the AI ethicist, yeah, of the human-centered AI ethicist, and that's a role that should be there. I think that is this brings these new jobs, and so we need also, let's say, people studying this too, in order to help the governments to create those policies, because the technology can, but then it becomes a social problem. Yeah, there has to be then a governance framework, and someone has to help create it.
Right. Thank you, ma'am. Thank you for the explanation.
I have one question. Can you tell me the role of SHA-256 and blockchain in quantum computing for cybersecurity?
What was the question? Sorry.
SHA-256 and blockchain
Yeah.
utility in quantum computing for cybersecurity.
Yeah.
So what role does it play when we talk about cybersecurity, the blockchain and the SHA-256 cryptographic mechanism?
Oh yes, so you can use a quantum emulation to hack, reverse engineer the password keys.
Okay. Thank you,
Yeah,
ma'am.
but like I said, but it's very, very expensive to access it, and only limited ones have it. But that's why it's really important that there is already a PQE governance framework for any company doing crypto.
Right. Thank you, ma'am.
Yes, there are a lot more questions. I see.
There is one more.
So, yeah, which countries are at the forefront of applying quantum technology sector, cybersecurity, healthcare, finance? So USA, of course. So here in Europe, and APAC. So that would be the region of China. Yeah, so those would be. And India is a riser, is a fast follower. Then, how does the role of finance professionals be impacted on quantum computing, and what skill foundations are needed to relevant finance industry increasing AI and quantum computing? So, number one, you need to understand business and finance. Then you need to be a mathematician. Then you need to have also a quantum computing, but of course a computing and programming background. Then you need to be also specialized in finance research methods. And then, of course, then in mathematics for PQC, as well then on cybersecurity. So on the PQC models. And then that's why I say that the job roles of the future are multidisciplinary. So the days in which, oh, I just did my bachelor in computer science and I got a job and then I'm fine, they're over. Yeah. So now you need to know different things. So I have both. That's why I applied to business and quantum computing. I applied to business, and I have both. You know, I have to study business. I have to study quantum computing, leadership and change. What would be then moving to these multidisciplines. Yeah, and that will create you a big high market value. I mean, if you want to show yourself for the future, I'm talking 5, 10, 15 years from now, so that you all are young. I mean, that's not nothing right now. Right now it's on research, but the next 10, 15 years, definitely. 5 to 10 years. I think that the main, Forrester made a survey study when they think that this will start to become relevant. For example, protection against quantum computer attack, crypto attacks, and they say 5 years this is going to happen. So if you start studying this right now, imagine the incredible market value that you're giving yourself versus anyone else that's not taking into this. All right. Then that's it regarding the time. So thank you very much. If you have any questions, like I said, keep them there. We can go through them on the next lesson.
Yes, sure, ma'am. Owing to time constraint, we will take this as a last question and continue with our next session. So here I am here to deliver vote of thanks on behalf of SVIMS and the organizing committee of this FDP. I take this opportunity to extend our heartfelt gratitude to Dr. Catherine for an immensely insightful and engaging sessions. Ma'am, your deep expertise, global perspective, and practical insights have broadened our understanding of how AI and quantum computing can transform cybersecurity and business practices. Your thought leadership and clarity of explanation have truly inspired both academic and industry participants present here today. I would also like to thank our esteemed participants for your active engagement, thoughtful questions, and continued enthusiasm throughout this FTP, throughout this session. So with this, we conclude today's first session. Thank you, ma'am.
Thank you. Good day to all. Bye.
Yeah, thank you. Bye. Now we welcome our guest of the second session. So due to unavoidable circumstances, today's schedule has been revised, and we are delighted to have with us our esteemed speaker, Dr. Ashwini Kumar Cherukuri, professor at the School of Computer Science, Engineering and Information System, VIT Vellore. With over 24 years of academic and research experience, Dr. Cherukuri's expertise spans machine learning, information security, quantum computing, and post-quantum cryptography. He has published more than 200 research papers with 4,700 plus citations and an H index of 34 on Google Scholar. He has also successfully executed multiple funded research projects worth over 10 million US, and he has guided 8 PhD scholars and several international interns. He has been continuously recognized since 2020 among the top 2% scientists in India in AI and ML by Stanford University researchers. In addition, he serves as adjunct professor at UCSI University, Malaysia. He is on the editorial board of several international journals and has received prestigious honors such as Young Scientist Fellowship, Inspiring Teacher Award, and Educator Excellence Award, and also a NAC Peer Review Committee member who has visited several reputed colleges across the country. Today, he will be delivering a session on Introduction to Quantum Computing. It is my great honor to welcome Dr. Ashwini Kumar Cherukuri, Over to you, sir.
Good evening, madam. Am I audible?
Yes, sir. Yes, you are audible.
And my slides are visible?
Yes, sir. Your slides are also visible.
Okay, so good evening, everybody. It's my pleasure to deliver this lecture on quantum computing on the occasion of ATAL Faculty Development Program on Next Generation Technologies in Action on the specific topics of generative AI and quantum computing, organized by Sadhu Vaswani Institute of Management Studies for Girls in Pune. So it's my pleasure as well as honor for receiving this invitation. And in the next 1 hour, 30 minutes or so, I will be delivering my presentation introducing various aspects of quantum computing. I understand from the organizers that the participants are quite enthusiastic, and as well as they are from different backgrounds, including management and other branches. So I will be delivering my lecture. I'll try to keep it less technical, as well as I will try to give as many examples as possible and then keep the presentation in a lighter manner. So before I proceed further and introduce actually the quantum computing, I was listening to the questions asked by some of the participants to the previous speaker. I understand that there are faculty from computer science, and I was told that there were participants from the management discipline also. So considering that, I have fine-tuned some of my slides. So before we proceed to the actual topic, all of us know, that when we consider a coin and which does not balance on its edges, it has two faces. So it has a head and it has the tiles, right? So imagine that there is a single coin lying on a flat surface. Then either it can face towards its edge or it can face its tiles up. Now imagine if I have two coins. If I have two coins, obviously I will have four states. In the sense, both of those coins can face with their heads up, or one of the coin can face its heads up, or else the other coin with the tiles up. Otherwise, one of the coin facing its tiles up and the other coin facing its heads up. Otherwise, both coins facing their tails up in the last scenario. So there are about four possible scenarios, meaning I am calling that scenarios as four possible states. So there are four possible states. If I have two coins, they would be facing these heads or heads tails or tail heads, tail states. So there are totally four possible states if I have two coins. Now imagine if I'm adding one more coin, that means third coin, then how many such combinations I would get, or rather scenarios I would get, or rather states I would get. Obviously, I would get 8 possible states facing one coin head, another coin head, another coin head, so on. I may have the last scenario, all coins facing their tails up. So these are the possible states, meaning I have 8 possible states with 3 coins. So if you closely observe, I am getting 2 coins. If I have 2 coins, then 2 square, which is 4 possible states. If I have 3 coins, it is 2 cube, having 8 possible states. Again, if you closely observe, the base value indicates either of the cases, head or tail, that means 2. Then total number of coins, it is 3. It is in the power. So totally I'm getting 8 possible states. Similarly, you can observe the same. I have head or tails 2 and then 2 coins. Then you have 2 power 2, which is 4 possible states. Now, why we are discussing about this? Somebody may get a question. We have some reason why we are discussing this. Now imagine if I proceed further. Imagine if I have n coins, then what would be the total possible states I would have? 2 power n possible states. Right? Why we are discussing this? Again, I will answer that doubt in the upcoming few seconds. Again, imagine I have a 6-sided dice. When you look at that standard dice, when we are playing, the dice can have either of these, the states facing up, either 1, 2, 3, or at the end 6. So meaning the possible states of a dice are 6 states, 1 to 6. Imagine if I have 2 dice, you can see all possible states of 2 dice represented in this particular diagram. So same thing we are putting in the form of a table. So dice 1, if I have dice 1 on column, another dice on the rows, so 1, 1, 1, 2, and so on. The same thing I have kept it in the form of a table. Right. Now, so if you closely observe, since each die has 6 possible states, there are about 36 possible states for 2 dice. If we continue the same pattern, if I have 3 dice, obviously I will have 216, meaning 6 to the power 3, 6 cube possible states. Now, when we proceed like this, if I have n dice, totally I will have 6 power n possible states. So one we have seen with regard to coin, the other one we have seen with regard to dice. So again, if you observe, if you have coin, it is 2 power n possible states. If you have dice, it is 6 power n possible states with n dice. Now, why we are talking about this? We are talking this particular coins or dice to identify or to quantify how much information coins and dice can carry. What does it mean? So let us say, take an example. Imagine I have a rainbow. So totally there are 7 colors, and these 7 colors can be represented or encoded by the possible configurations of either 3 coins or 2 dice. Meaning what? If I want to encode all these 7 colors, I should use either 2 coins, 2 dice, or 3 coins. How can I use it? So let us say, imagine I have color red. Color red, I can encode it as head, head, head if I am using 3 coins. If I am using dice, I can encode it as 1, 1. Similarly, if I want to encode color orange, I can encode in the form of 3 coins as head, head, and tail. If it is dice, I can encode it as 1, 2. And you can proceed further: yellow, green, blue, indigo, and violet. Right? So this is how I am going to encode the colors of a rainbow. So meaning what actually I'm doing, if I have 3 coins, first heads, then tail, and then tail again, right? What it is going to represent? It is going to represent the color green. So head, tail, and tail, it is going to represent my color green, right? So if it is dice, I'm going to represent in the form of 1, 4, right? So if you closely observe, if I want to represent a particular color, if I am representing in the form of coins, I need 3 coins. If I am representing in the form of dice, I need 2 dice. So what this finally infer? A coin carries less information than die. Because of that, I need more number of coins, less number of dice to encode colors of a rainbow. So that is the reason why, if you observe, it takes 3 coins to distinguish the 7 colors of a rainbow, whereas I need 2 dice to distinguish the rainbow colors. What is all this giving a hint or a clue, or what is this is related to our current topic of quantum computing? The final conclusion is something with 2 states carries the smallest amount of information possible. What is that which is having 2 states in the world of computer? The classical bit, which is the fundamental unit of classical computer, which represents the information in the form of 0 or 1. In the coin analogy, either it is representing in the form of either head or tail. The classical bit represents the information with the two states, either 0 or 1, either off or on. Right? Everybody knows this. So conventional digital computers have only two states, which is 0 or 1. Okay, so what does it mean? What is that next you wanted to tell? Meaning, imagine if we have something else which can carry not two states, but rather more states. What it will do? It can represent my information in a smaller number of states. It can represent a large number of information. That's what we have seen with the case of 2 coins or 2 dice as well as 3 coins, right? So the fundamental basis or fundamental difference between a classical computer, quantum computer lies from this particular observation of a classical computer. We can say a kind of a coin like representing on, off, head, tail, whereas a quantum computer is like, with a more number of states representing like a dice. Right? So it's a very, very, very primitive example, but to get a feel of something which is carrying us with the two states would carry smallest amount of information, whereas if it can have more number of states, it can carry large number of information. That's what is the basis of our entire quantum computing. If we observe the way the computers have evolved, especially all of us know that the modern digital computers have evolved after World War II. But if you observe during this evaluation, especially in the last 4 or 5 decades, we have a tremendous progress. But however, computers have come by the term of computing, it has come from a long way. Earlier, if you say computers, now present day we say computers, we all know the modern gadgets. But the first computers were people, and it's not the machines. The people were performing the computations and calculations. In fact, the term computer was dated back to early 1600s before our digital age started, meaning those days computations and calculations were performed by the people. But even though we have humans were placing the calculations in the modern history as well, especially with the NASA, the early days of NASA, where in which people were doing the manual calculations. And subsequently, post-World War II and 1960s onwards, first mechanical computers, then electrical computers and electronic computers have taken the evolution, and they have taken the entire computing environment. Again, there is a huge history of the way these computers have evolved in terms of their sizes, in terms of the memory, in terms of the processing speed. There is a huge evolution that has come, and now from larger room sizes to handheld devices, we have the computers that got evolved. So in all these computers or the modern digital computers, what is the fundamental unit? The fundamental unit is a classical bit, which is the fundamental unit of representing, processing the information. So we can encode whatever the information we would wanted to encode, store, process using the bits. And fundamentally, we will use words, characters, and even pictures would be encoded and stored in the form of bits. But once you represent the information in the form of bits, we process those information using various logical operations, whereas for a computer, they are nothing but logic gates. There are several logic gates like OR gate, AND gate, NAND gate, like that. There are several logic gates. So from bits to gates, gates to registers, registers to circuits, we have various fundamental units or fundamental building blocks for the modern digital computers. Now, all that is fine. So this is all about evolution of computer. Now, every day we are listening the word quantum computer. So what is quantum computer? If you observe a classical computer is fundamentally based on or manipulating the fundamental physical properties and classical mechanical properties. And quantum computer actually uses quantum mechanics and quantum physics behind its computation, and hence it gives us massive parallelism, massive amount of parallel computing through quantum physical properties. What are those quantum physical properties? Superposition, entanglement, and decoherence, which are not there in the classical computers. So which are against the classical computers, quantum computers have these phenomenon, and because of which they have a huge, massive parallel computing power. And because of that, we have several advantages now. Again, there are several couple of disadvantages because of which the entire security community is little worried. And on the other side, there are various business use cases of this massive parallel computing where people are trying to leverage quantum computers and try to solve the problems that conventional classical computers are not solving. So meaning what? You have certain business use cases which can leverage this massive parallel computing, and there are certain challenges where computer scientists and others are trying to solve because of this massive parallel computing. So both we are witnessing today. Yes, now what are the features of this quantum world? Or in the sense we said, the quantum computers follow the physics that are coming from quantum physics. What are those features? If we observe, a few seconds back, I said you are having fundamental unit of information is bit, and then we have gates, we have registers and all that to perform computations. In a classical computer, we perform these computations on real numbers. However, in quantum computers, the computation happens on the complex numbers. So those especially coming from the different branches of the management and others, we have in the number systems, we have natural numbers, we have real numbers, we have integers, but at the same time, we have certain set of numbers called complex numbers, where in which you have a number having a real part and also has an imaginary part. So quantum computers deals with the complex numbers. In fact, real numbers is a subset of complex numbers. So classical computers are able to deal with only real numbers, but not complex numbers. But whereas the quantum computers, the base itself is the complex numbers. So quantum mechanics is different from the other branch of sciences because this is using fundamentally the complex numbers. Then the other features of quantum physics that is coming to quantum computing is computing from moving from single state environment to superposition of state environment. So this is another interesting keyword that every day we use, even whenever we are reading about quantum computing, the word called superposition. What is superposition? A superposition means, to understand that every object exists in a unique place, in a well-defined state, even when we are not looking at it. Although this is true for large objects, quantum mechanics tells us that it is false for objects that are very small. Meaning what? So take an example. I keep giving this example whenever I give my lectures. So at the moment, I'm doing one particular task of delivering my lecture. At the same time, my brain is also doing several other thought processes, which includes, coordinating several things, right? So meaning what? If you look at if you look at a particular person as an individual entity or an object doing one particular task, but at the same time, if you look at the brain, is doing multiple parallel activities or multiple parallel tasks. So meaning a classical computer at a given point of time would be performing only one particular task, meaning, processor would be executing one particular instruction coming from the operating system or the application. But whereas a quantum computer can perform a parallel activity of executing multiple tasks or multiple states. That's what is called superposition. So if we say that an object is in superposition, it is simultaneously in multiple states at the same time. Meaning, right, we say that I'm doing multiple tasks at a time. I'm doing parallel tasks at a time. So this is the exact word in the quantum computing called superposition. Meaning what? We are simultaneously in multiple states at the same time. At a given point of time, an object would be there in multiple states, right? So, but what happens when we say we are measuring that particular object? From the superposition state, that object would get collapsed and called it will settle down to a particular well-defined state. So from superposition, it will settle down to a single state through the process called measurement. Right? So take an example. Imagine when there is a lecture going on in a class, if you observe a student, physically the boy would be there, boy or girl would be there in the class, but they would be thinking multiple thoughts at a given time. But the moment we ask a question, the student will come to an alert and then try to focus on what we are asking. So meaning what? The brain is in a superposition state, doing, thinking, multiple activities at a given point of time. But the moment you post a question, it coming to a particular single state called, we call it as a measurement state, or we call it as a collapsed state. So that's the analogy that I can give whenever I give my sessions on this quantum computing. So superposition, meaning we are there simultaneously in multiple states at a given time. A measurement is nothing but when we observe or when we try to finally compute and calculate and measure the superposition state, it gets collapsed to a single state. And the next feature that is coming to the quantum computing from the environment of the quantum physics is moving from locality to the non-locality, right? So what is the fundamental notion or fundamental objective or fundamental basis for the current modern science is that we know that objects that are directly affected are only those that are near to those objects. Meaning what? In operating system also, we say that a particular memory location, if it is referred by a processor or an operating system, it is more likely that the nearby locations are also would be referred. So it's a called principle of locality. But whereas in a quantum world, we move from locality to the non-locality world in the sense that two particles can be connected, or we can also say the same connected word as entangled, even though they are at different places, even though they are at far different places. So we move from locality to the non-locality. This is one of the other feature that is coming from quantum physics to the quantum computing environment. Then another interesting feature that is coming to the quantum computing environment from the quantum physical features is we are going to move from deterministic laws to the probabilistic laws. Meaning what? Say, take an example. We are moving from say, take an example. When we have an algorithm in a classical world, when we have an algorithm given a particular input, given a particular the amount of time, an algorithm would execute and produce always the same result. If the same input is given, when we execute the same algorithm, it produces the same output. But whereas in the case of quantum, the output is not a deterministic output, rather it is a probabilistic output. So that is the reason why, if you observe to which specific state a superposition state will get collapsed when it is measured, nobody knows. So it's a probabilistic in nature. So meaning what? If I throw my coin, to the air, when the coin flips, it is kind of a superposition because it is flipping between head and it is flipping between head and tail. But when the moment you measure it, it would become either head or tail. But you are not sure whether it would come to the head state or whether it would come to the tail state. We do not know, right? So it's kind of a probabilistic. So here also the outcome would be probabilistic in nature. Again, we are going to have one more property called moving from certainty to the uncertainty. As I said, the outcome is highly uncertain in the case of quantum computing. So the laws of quantum mechanics also inform us that there are certain inherent limitations to the amount of knowledge that one can ascertain from a particular physical system. It is arised from a property called Heisenberg uncertainty principle, which says that there is a fundamental limit to the precision with which certain pairs of physical properties of a particle can be known simultaneously. This is called uncertainty principles. This is the fundamental definition. What does it mean? It indicates, meaning what? If we more accurately we try to know a particle's position, then we will know less accurately about its momentum. That is what is a loose definition for the given uncertainty principle. What does it mean? So take an example. Imagine there is a train moving, meaning what? It has some momentum. Now I want to measure its position. When it is in movement, can I measure its position? No, train, car, or bus, whatever the object that has the momentum and it is moving. And if I try to measure its position, obviously I cannot measure. The moment I measure from that, the time that I was trying to measure to my actual measurement, the car might have moved because of its momentum. So meaning what? If it has a momentum, the less I would know exactly about its position. Right? That's what is called uncertainty principle, meaning which the more accurately we know about the position, then we know less about its momentum, right? Or even vice versa. I gave the example of the vice versa, right? This is the another interesting feature that is coming from quantum physics to the quantum computing environment. So because of all these features, quantum computing is becoming unique. So what are the features? Just to summarize, we are moving from real numbers to the complex numbers. We are moving from single state objects to the superposition of state objects. We are moving from locality to the non-locality of the entangled objects. We are moving from having a deterministic outcomes to the probabilistic outcomes. We are computing from a certainty environment to an uncertainty environment. These are the different features which are motivating factors or which are the basis for quantum computing. I hope all of you are able to follow. Are there any doubts so far? My pace is fine? My discussion is fine? Are there any doubts so far? Whatever we have discussed?
If anybody wants to ask any question, they can raise. You can raise your hand. Yes, sir. We can.
Yeah, I see a couple of questions.
Yes.
Can you please explain any of the quantum algorithm like SHAR algorithm? Of course, I can explain, but now considering the time we have, SHAR algorithm is an interesting algorithm. I know this algorithm, is one of the fundamental algorithm which was proposed in 1992 or 93, where even people were not having any kind of quantum computer. So this algorithm is the one which is making many of the our entire security industry sleepless, because of now today we have quantum computers. What this algorithm is trying to do is it is trying to solve one of the fundamental problem in cryptography, wherein which that problem is the basis for entire public key cryptography algorithms that are providing security to our online transactions, that are providing security for our digital signatures, etc., etc. So because of that algorithm, now all these public key cryptography methods, protocols, they are in danger. So and that is what actually people are trying to build post-quantum cryptography algorithms. And now we are at a particular level of standards that have come recently from NIST, and the solution builders are trying to build protocols and the other security products from PQC standards that are coming from NIST. So SHAR algorithm is fundamentally an algorithm that is solving a problem called finding prime factors of a given number. It appears so simple in the sense that just to give a glimpse of what is this algorithm is doing. Imagine if suppose somebody gives you two variables like XY and asking you to find product of it. So you can always find easily, very easily X into Y. But what actually is the challenging factor is if suppose somebody gives you Z, asking you to find the factors of Z, meaning X comma Y, this problem becomes challenge. In the sense, this is a computationally easy problem. This is computationally tough problem. This problem becomes much more tougher if suppose somebody is asking you to find not simply X and Y, but these X and Y should be prime numbers, right? Meaning what? Asking you to find the prime factors of Z. Of course, if suppose somebody gives you a single digit, two digit, three digit numbers, this is relatively easy. But what we are talking about the complexity in terms of numbers which are of 200 digits, right? Numbers which are of 150 digits. These type of numbers, even the current supercomputers also cannot solve. And because of that, the Shor algorithm, because of the Shor algorithm, which is providing this solution to this problem, in fact, on this particular premise, where in which we don't have solution for this, based on this particular problem, we have the security algorithms from public key cryptography. And now, since the Shor algorithm is solving this problem, all those algorithms are becoming vulnerable. So that's the point. That is the challenge. And entanglement example related to quantum computing. Of course, I will talk about it in the next few slides. So yeah, I think people are fine. And sir, it's good that you are considering persons from management. Yeah, I think management, I would give some of the perspectives at the end before my concluding their talk. So as I said before, let us continue. Features of the quantum world, we have talked about it. So if you observe, the bit, we said fundamental unit of the quantum computer is the bit, which stores the information 0 or 1. Now, when it comes to quantum, what is that bit would be, how it would be, right? So if you observe for that particular purpose, if you notice an electron, which may have two spins, either it could be having a clockwise spin or a counterclockwise spin. But a quantum computer, you can think it as an electron which has a mixed state in the sense. So take an example. I have a classical bit in the form of on, off. So when it is on, I'm saying it is 1. When it electric pulse, it is off, it is 0, right? When it comes to a quantum computer, you can see on the other side of the slide, where a small GIF image is shown. How it actually gets implemented is through electronic spin. So in the sense, if you notice, that electron is in the form of both 0 as well as 1. So in the form of left spin and right spin. Another crude analogy I can tell is, kids play with the spinner, right? Widget spinner. So the spinner actually rotates, right? Either horizontally or vertically. You can think of a spinner which can actually rotate both horizontally and vertically. That's a kind of the fundamental unit called a qubit. So a quantum computer uses the qubits. Quantum computer uses qubits, which are the basis for storing the information, right? So in the sense that it has the blend of possibility of being 0 as well as 1, right? So as I said, in a conventional computer, it takes 4 separate calculations to run through all possible combinations of two bits. If I have 2 bits, 0, 0, 0, 1, 1, 0, 1, 1. So I have 4 separate calculations to run through all the possible combinations of the two bits. However, in the case of quantum computer, you will have, so you can see here on the left side, if I have 2 bits, I have 0, 0, 0, 1, 1, 0, and 1, 1. I'm having all 4 possible combinations, but I have to go through them in a sequential manner. Whereas if you notice on the right side, if I have 2 qubits, I will have 0, 0, 0, 1, 1, 0, 1, 1, all 4 possible combinations at a time. You see the GIF animation, which shows 4 combinations of bits coming sequentially. On the other side, 4 combinations of qubits coming at a time, being available at a time to the programmer or to the user. Meaning what? If you have all 4 states at a time available to the programmer, we can do computations very easily, very faster manner. Rather than doing sequentially, we can do in parallel, right? That's the beauty of the qubits. So the concept or the theoretical analogy of these the qubits were there earlier. People were struggling. How do they implement it? But thanks to the technology from the various physics scientists, now people are able to implement the qubits having these properties through various physical the structures, right? So this is the quantum speed up because of the availability of all possible state at a time, right? Now the slide actually shows only 2 qubits or 2 bits. Now you can give the same analogy for 3 qubits, 4 qubits or 5 qubits. The more number of qubits, more number of possible states, and all of them being available at a time to the user or the programmer or the developer or whoever it is, right? This is called quantum speed up, right? Now, if you closely differentiate the classical computer and as well as the quantum computer, in terms of quantum storage, you have bits which are manipulated through the electric pulses, whereas in the case of quantum computing, it is through the spin of electron in the form of qubits, right? So information, how it is processed, as I have already said, you have classical gates. In the case of quantum analogy, simple analogy to the classical gates, we have quantum logic gates. If you observe, next to the gates, you have circuits. In the case of conventional computers, all these classical circuits are governed by classical physics, whereas in the case of quantum computers, these gates are governed by quantum physics and quantum mechanics, right? How the information is represented in the form of either 0 or 1. But whereas in the case of quantum 0, it could be 1 or it could be both of them. That is the beauty, or that is the advantage that the quantum computers are providing. Now, any computer by means, it has fundamental mathematical theories. So if you observe, the Boolean algebra supported by so classical computers are supported by Boolean algebra, whereas in the case of quantum, they are the linear algebra over the a mathematical space called Hilbert space. Its complex number space is called Hilbert space. That anyway, it's a mathematical aspect. So next, if you observe the advantages, there is no limit of copying or measuring the signals in terms of classical computers. However, in the case of quantum, because of the availability of the all possible states, obviously the quantum computers are highly faster than the classical computers. In the case of the disadvantages, certainly the classicals are slower than quantum computers, right? But when you look at the quantum computers, they also have certain disadvantages as of now. Now there is a lot of noise. There is a lot of noise because of the external environment, and these quantum computers are prone to the errors because of the noise coming from the external environment, and hence they are fragile, right? So these are the basic disadvantages with the quantum computers. And now what people are developing is called noisy intermediate state quantum computers, NISQ quantum computers. Down the line, people are expecting that we will have noise-free quantum computers that we need to wait and watch, right? So these are again the slides which are talking about the fundamental unit of classical computers is bit. For the fundamental units of the quantum computers are called qubits. How do you say it is a qubit? It is represented through a notation called bracket notation. We write in case of classical bit, we write it as a 0 or 1. Whereas in the case of quantum computers, we write that the state of the qubit either in the form of 0 or 1 through this particular notation called bra and ket. Right? This is only for the notation. Those who are not belonging to the computer science or the other related disciplines, I think, that for them it may be something new, but for the others of computers, I think these are this one. As I said, you have given a 2 qubits, you have all possible qubit states, 0, 0, 1, 0, 0, 1, 1, 1, all being available at a time. So if I have a 2 qubit system, then obviously I will have 4 basis states. We call these as states of the qubits, and these are all called basic states. And every state would also have a complex constant. We represent that with different variables. So meaning every qubit state would have a particular alpha, beta, gamma, or A00, A01, A10, A11. These are all called complex constants, and every basis state would be associated with one particular complex constant. Why do we require it? And actually, this would not be there in the case of classical. But however, when it comes to quantum, every qubit state would have a complex constant. Why we require complex constant, that we will discuss in the upcoming slides. So imagine if I have 3 qubit system, as I said, you have all possible states of 0, 0, 0 to 1, 1, 1, all being available. That means 2 power 3, that is 8 possible states, all are available to the programmer at a time, or the application developer at a time. And because of that, we can see a massive parallel computation available. So I gave 3 qubits. If suppose I have n qubits, obviously I'm going to have 2 power n possible states. It appears very simple, or with a small number of n. So take an example. Imagine if I have n is equal to 64, meaning what? I have 2 power 64 possible combination. You see here, what would be the 2 power 64 number of possible states? Can somebody read this number? It's very difficult. What is this exactly? If you want to quantify this number, 16 lakh, 16,000, or 16 crores, or 16 billion. So you see the number of zeros you have. So this is a very huge number, right, of possible number of states that one can have with a 64-bit quantum computer. 2 power 64, all possible states being available to the user at a time, parallelly at a time. So this makes this availability of all possible states makes the people to solve any kind of a complex problem which are not solvable by conventional computers, that can be solved by the quantum computer. To just give a glimpse, a typical security problem, if it is taking about millions of years to solve by a classical computer, a quantum computer can solve it within a fraction of hours. That's where the problem comes, right? So next, you see another important feature of the quantum computer, we said about the superposition. Superposition means what? Given a particular qubit would have either 0 state or 1 state, or it can be there in a superposition of both 0 and 1. So whereas a classical computer with a classical bit would be there either 0 or 1, whereas a qubit would be there 0, 1, and superposition of 0 and 1. That is what is the ability or strength coming from the quantum physics. So how do I represent a qubit which is in the form of a superposition? I would be representing in the form of 1 by root 2, the qubit 0 and qubit 1. This is called superposition state. This is called superposition state. Now imagine if I have 3 qubit, then what would be the superposition state for a 3 qubit system? So you can see here 1 by root 8, 0, 0, 0 to 1 by root 8, 1, 1, 1, 1. So this is the superposition state of a 3 qubit system. Similarly, you can have an n qubit system having all qubits in a superposition state. Next, we have another important property of a quantum computer called coherence. Coherence or decoherence, especially quantum decoherence, means loss of superposition, right? When what we said superposition, a qubit could be there 0 or 1, or being there 0 and 1, right? So whereas in the case of decoherence, the quantum computer or the qubits would lose the superposition state, and resulting because of the interaction with the environment. So the loss of information happens by the qubits because of the environmental effects. This is one of the reason, or this is one of the main factor we call quantum computers are extremely fragile. Next, another feature or another basis of quantum computing is the measurement, which is quite opposite to the superposition state. So when a qubit is in a superposition state, it is there in the all possible states that a qubit should be. But when you measure it, it gets collapsed, right? It gets collapsed to either 0 or 1. In the sense, a qubit will be, we said, it could be either 0 and 1 in the case of superposition. But when you measure it, it gets collapsed to either 0 or 1. But sir, whether it gets to 0 finally when I measure it, whether it reaches to 0 or whether it reaches to 1, that is based upon your complex coefficient or the variable that what we have assigned previously. You know, a few seconds back, I've talked about the variable alpha, beta, gamma, or A0, A1, like that variables. So if the variable we have, the square of the variable decides to which state the qubit would settle down, whether it settles down to 0 or whether it settles down to 1. The square of this particular variable defines the state. So meaning, you know, you are not sure till you measure it whether it reaches to 0 or 1. So we have talked about qubits. We have talked about the superposition of the qubits, meaning a qubit could be there in the possible combinations of the states. When you measure it, it settles down to either of the state, but to which state it settles down, it is based upon the complex variables that are assigned to each of the state. That's what we have discussed. Next, followed by the qubits we have is the quantum gates. It is similar to the logical gates that are there with the classical computers. We have the quantum gates. The quantum gates here, we have multiple quantum gates called one of the example gate that what we have is the Hadamard gate. What is this Hadamard gate is doing is it takes the single qubit as an input and put it in the form of a superposition state. So as I've already said a few slides back, if you take a qubit, it could be there in the superposition state. How do you achieve superposition state? If I apply this Hadamard gate over my qubit, it reaches to the superposition state. So gates will help us to move or to transform the given qubit data to whatever that we require. Next gate we have is the Pauli X gate, where in which you have, if you apply the Pauli X gate on 0 qubit, it reaches the 1 state. If you apply it on 1 qubit, it reaches to the 0 state, meaning it flips the given input. That is the job of Pauli gate. Similarly, you have C0 gate, which is called as controlled NOT gate, and it is a 2 qubit gate. What we have seen, Hadamard gate or X gate, they are all single qubit gates. The C0 is the two works on the 2 qubits. So you can see the logical operation. If you have 0, 0, when you apply C0, it reaches 0, 0. If you apply 0, 1, if you take 0, 1, apply C0, it reaches 0, 1. Whereas if we take 1, 0, if you apply C0, it reaches 1, 1. If you have 1, 1, it reaches 1, 0. Meaning what? If I say this is my control qubit and this is my target qubit, my target is remaining same when my control is 0. But when my control is 1, my target is getting flipped. That is the job of this particular gate called C0 gate. So it acts on 2 qubits, the C0 gates. So if your control qubit is set to 0, target remains same. If control qubit is set to 1, target gets flipped. So this is the job of C0 gate. Like this, we have several gates that forms the basis or that provides the the computational ability on the quantum computers. So you have seen Pauli X gate, we have Pauli Y gate, Pauli Z gate, Hadamard gate, which gives the superposition, phase rotation gates, S gate, P gate, T gate, then C0 gate, control Z gate, swap gate, Toffoli gate. These are all the gates which are the fundamental for quantum computers, especially those who are from computer science or electrical or the electronic background. They all know that we have classical gates. Now from fundamental bit, we are operating these particular gates so that we are able to run our computations, we are able to perform our calculations. Whereas in the case of quantum, these are all the gates. So you can see the different gates. And fundamentally, if you observe these gates, if you try to program, we actually play with the matrices, corresponding matrices. Meaning what? Every gate is encoded in the form of a matrix. So you provide the input, and that input operates on the particular gate, means you apply corresponding matrix operation on the given input. So that is the fundamental when we do it, when we write the programs. So now we have seen qubits, we have seen Q gates. When you have multiple gates, or when we have a sequence of quantum gates, what they form quantum circuit. Like classical computers, when we take the gates and when we combine them, we'll have the circuits, right? So in the similar manner, we have quantum circuits. If you see here, I have a qubit 1, I have qubit 2, I have qubit 3. Now I can see that there is a Hadamard gate, there is an S gate, there is a Toffoli gate or a T gate. Then there is a T gate. Then the output is getting given as an input to the next gate. So this is how this is my swap gate. So these are all forming a quantum circuit. So similarly, if you observe this in this particular circuit, there is a diagram which talks about the measurement. So if you see here, a qubit is in Hadamard, meaning superposition. After that, it is going for measurement. So this is how we can read the quantum circuit diagrams. So now we have seen bits, we have seen qubits, we have seen Q gates, we have seen what is a quantum circuit. And when we play with those circuits, we can do that with the help of quantum algorithms, right? So we need to write an algorithm so that we can exploit these qubits and the quantum circuits. So for which we need algorithms. What are the algorithms that we can do? We have several algorithms in quantum called one. Somebody has already asked about the Shor algorithm. There is an algorithm called Grover algorithm, which is mainly meant for Shor algorithm is mainly meant for solving the prime factorization problem. Grover algorithm is meant for solving unsorted or unstructured search problem, right? So how do I search in a faster manner in a given unstructured database? So there is an algorithm called Grover algorithm. So these algorithms are fundamentally available algorithms, like there is Simon algorithm. There are algorithms like this. On top of that, people are trying to build algorithms so that we can exploit these quantum properties of qubits, Q gates, and Q circuits, right? By exploiting that Q gates or Q circuits, what is that we will achieve is we will achieve the parallelism. We will achieve the entanglement capability. Meaning what? When a qubit, I think somebody has asked, 2 qubits can be entangled. Meaning what? Measurement of 1 qubit will affect the outcome of the other qubit. Meaning what? In a loose term, I can say entanglement is like a kind of a correlation. Correlating, you can correlate 2 qubits. When you measure 1 qubit, obviously the outcome of the other qubit also would get impacted, right? Now, what is the difference between the algorithms that are there in a classical environment? Since we talked about the quantum algorithms, when it comes to the measurement of these algorithms, generally for classical algorithms, we talk about algorithms that are we look for the algorithms that are solving the problems in a we will say that these algorithms are deterministic algorithms and they execute or solve the given problem in a polynomial time. And the algorithms don't produce any kind of error and there is no randomness involved. Meaning what? Imagine if I perform a matrix multiplication operation, which is a deterministic algorithm, you perform any number of times, you get the same output, right? Whereas in the case of quantum, we measure them as these quantum algorithms are measured as bounded error quantum polynomial time called BQP time.
Sorry to disturb you. There are certain questions. Sorry, sir, I'm disturbing you. There are 3-4 questions in the chat box. Can you address them?
Okay. Wait. Yeah.
People are waiting. What are the possible research areas in the field in India?
I will. This is in. Okay. This is I will do that. So
Okay.
yeah, sure. So, when it comes to measuring these algorithms, we look for the algorithms that run in a polynomial time. When it comes to quantum, we look for the algorithm. We say that these algorithms are bounded error quantum polynomial time. Meaning what? These quantum algorithms run in a polynomial time with the bounded error. This is what is very, very important. You look at the case of classical, there is no randomness, there is no error. Whereas in the case of quantum, you are having the algorithms that run with a bounded error capability. Meaning what? Imagine if I am running an algorithm 3 times, it should produce at least 2 and above. At least it should produce 2 and above number of times correct result. Meaning what? I'm giving, in the case of a classical, if I'm running my algorithm 3 times, it should produce 3 times, it should produce the same result. Whereas in the case of quantum, there is a room for error, and which is given tolerated as a bounded error, right? So that boundness is at least 2 and above, it should be correct. That's what is called bounded error quantum polynomial time. And then this error, what will happen is we will try to reduce it by performing repeated computations. So the best examples what we have is, as I said, Shor algorithm and Grover's algorithm. Now, so how this type of images people would have seen already in the news and other magazines about how does the quantum computer look. This is generally every day we see in the news or wherever we try to see about a quantum computer. This is about IBM quantum computer, which is a 53-qubit superconductor quantum computer. If you look at the various platforms that are available now, as of now, to the academic community, there are the platforms especially coming from IBM, which is IBM Quantum, and this particular is programming interface provided by the IBM is through Qiskit, and it supports the Python. And there are various educational typical use cases for education purpose, implementing the quantum gates, implementing the quantum variational algorithms. In case of Amazon, they have a platform called Bracket. Of course, it is pay as you go, and it supports Bracket SDK. Of course, we can have the algorithms and various use cases such as optimization, as well as we can also run hybrid algorithms such as quantum classical algorithms. Even from Microsoft Azure also has a platform which is pay as you go, which supports the programming through Q# as well as Python, right? And we can there are various use cases from quantum chemistry, algorithm simulations, and all. These are all given to academia. Similarly, from Google, we have Quantum AI, of course, for research purpose. There are various use cases in terms of quantum walks. There are algorithm benchmarks that are there. And people talk about quantum supremacy, meaning what? It has achieved the highest, as per the current standard, it has achieved the quantum superposition states. Similarly, D-Wave also has the platform. Xanadu cloud platform is there. Through Pennylian, people are writing the programs, again, to solve quantum machine learning problems and chemistry problems. These are some of the platforms that we have. And before I proceed and address the questions, I would like to address some of the myths general public or people have. People think that, few years, couple of months back, even people thought that quantum computing would not be commercially available for next 10 to 15 years, but it is not so. Now quantum computers are commercially available, and even whether to have a quantum computer on campus, it is not required. We can access them through the cloud platforms that are already there, and that is how the researchers and government agencies and then the enterprises are trying to access the quantum computing facility. Then another myth is about a qubit can be there 0 and 1 at a given time, same time. In order to understand, even I have mentioned that a few slides back, I've mentioned that a qubit could be a classical bit could be in a 0 state or a 1 state. When it comes to quantum, it could be in both states. What does actually it meaning is that a qubit is When I say that qubit is in the 0 and 1 state, it is in a position of superposition state, meaning it represents the value for in the form of a linear combination of real and imaginary numbers that changes by a computer program or through a particular circuit. Meaning what? If I have a qubit Q1, I say 0 or 1, or it is in the form of a linear combination of 0 and 1. That is what is meaning of that. So it is either 0 state or it is in 1 state, but it is in the combination of 1 state as a linear combination of these complex variables. Right? This is what is meant by superposition state. It is not that simply we say 0 and 1. So this is another myth. Of course, the other branches of people may not be of that much pay keen attention, but whereas for a computer science students, this difference or this understanding is very much required. Quantum computers replace classical computers. People may think that, but in fact, classical computers would certainly say, take an example, if I have a typical spreadsheet program or a typical, the Office, Microsoft Office, Word program or whatever it is, I can use always my classical computers. Quantum computers are needed, are required to solve highly complex problems, right? That are not solvable by the classical computers. I don't require a quantum computer to perform my day-to-day computations, my day-to-day algorithms, or to calculate my simple tasks of financial calculations and all that. So they require certain, if I have some complex problems, which I'm going to talk about after a few slides, there only you require quantum computers. It's not that, next another 10, 5, 15 years or 5 years, all classical computers will be replaced by quantum. It's another myth. Again, quantum computers solve all classical problems. This is another myth. We require classical computers to solve all classical problems. Only those problems that are not solvable by classical computers only we require quantum. Quantum computers will destroy encryption or provide. I will pass. Quantum computers will destroy encryption. Partly it is correct. Again, partly it is not, in the sense it will completely destroy or give threat to encryption algorithms such as public key encryption algorithms, not a symmetric key encryption algorithms, meaning private key encryption or symmetric key encryption algorithms. Of course, quantum computers will make an impact, but they cannot destroy. Similarly, quantum computers will provide complete security. Again, this is another myth. It's not so. So it is only for computer science people or only for physics people. Again, another myth. Now we have. I'm going to talk about various fields in which almost all branches of people are going to gain benefit out of the quantum computers. Right. So this is another slide which I think similar to the one which I've already mentioned about various companies that are there in the market, and they have their own quantum computers. On what technology these quantum computers are built. Say, take an example, IBM quantum computers are built from superconducting technology, whereas the other Microsoft company, Microsoft has their qubits built from topological properties. Their trapped atom properties are used by Xanadu. Similarly, photonic devices are used by PsiQuantum. So like this, there are various technologies behind building qubits, and each company is using as per their requirement. Now, if you observe the quantum computing market, it is going to significantly increase globally year after year. As per the estimations, it is expected that it would touch about more than $5 billion by value by 2032 in North America alone. Globally also, it is going to touch by 2032 $65 billion. It's a huge market that is evolving in terms of quantum computing. If you observe the use cases, there are several use cases. One of the use case is about portfolio optimization. Suppose I wanted to optimize my financial portfolio in a way that I would reduce the risk. Certainly, the quantum computers would provide better solutions. Similarly, in a complex financial environments, how do I manage the risks? Again, this is also going to be provided use case by the quantum computers. Similarly, in the case of cryptography, as I said, there is a threat from quantum computers. At the same time, we are going to have some solutions coming from quantum computers towards cryptography and finally to the security per se, the cyber security per se. And as well as the machine learning side, we are going to have quantum machine learning algorithms which are trying to augment or support the classical machine learning algorithms or optimize the classical machine learning algorithms. So these are some of the use cases. And if you see the larger use cases, several enterprises are already either becoming quantum ready or are making themselves quantum ready. You can see almost all large sector players, either in terms of financial sector, whether in terms of healthcare, whether in terms of transport sector, whether it is whether in the case of telecom, whether in the case of space technologies, whether in the case of the oil and energy sector, almost every sector, if you notice, they are the major companies, they are trying to leverage the quantum computing for their day-to-day operations or their R&D operations or for their future the use cases and then the future ready purpose. And hence they are actually trying to hire as much as talent as possible. The slide shows almost all leading players in every sector. So in terms of healthcare, you can see Novartis, you can see Pfizer, you can see United Healthcare. In the case of financial, you have PayPal, you have HSBC, Morgan Stanley, JP Morgan. In the case of transport, you can see almost all leading transport companies like BMW, Toyota, Ford. In the case of space, you have Boeing, Airbus, almost every company in every sector, they are trying to leverage the quantum computers. Again, this slide, which is taken from the infographic, is taken from the McKinsey report, wherein which you can see the various quantum computing or quantum related algorithms coming from, say, whether it is solving a factorization problem or algorithms related to simulation, algorithms related to quantum optimization, machine learning and algorithm, and then search problem. So these are all the various algorithms or algorithm categories, and you can see various application or use case scenarios, like whether it is a finance, life sciences, aerospace, chemicals, transport, automobile and manufacturing industry, various industries. If you notice, what would be the impact of these algorithms or the algorithmic category. So especially if you look at the factorization algorithms, as I said, it is going to make a disruptive impact on the finance. The reason is simple. We perform day-to-day a lot of online transactions, banking transactions. All those transactions backbone is cryptographic algorithms. So breaking these cryptographic algorithms obviously would make a disruptive impact. That is the reason why you can see the infographic indicates that the quantum computing has a major impact on the finance. Similarly, you can also see the optimization algorithms are also going to make a significant impact on the finance. The reason is that we are going to have a low risk and better optimize our finance portfolios. Like this particular infographic, those who are interested, you can actually Google it through and ask the McKinsey report of use cases. You can get this infographic. Similarly, you can also see, this is another in terms of quantifying the business value of these, the algorithmic categories of quantum computing and in various sectors of pharma, aerospace, chemistry. You can see all the figures. Those who are from finance, management, and business sectors, you can see the business value of all these categories that the quantum computers would bring to various sectors and various algorithms. Say, take an example. In the case of optimization, aerospace has going to have about 20 to 50 billion dollars of value, especially for the optimization purpose itself. So these are the various use cases that we have. So among the industry sectors, the finance industry is the first or the most earliest industry adopting the quantum computer. As I said, fundamentally, number one, because of the security reasons, but also not only that, it is also about the various use cases. Within finance itself, you can see various use cases in terms of portfolio selection, capital allocation, transaction settlement. Like this, we have various use cases within the finance sector itself, right? So because of that, there are leading players in the finance sector which are deriving benefit or value out of these the use cases. Similarly, in the case of automotive, again, optimization, simulation, and numerical simulations and all, we have various use cases, right? As I've shown, BMW and other Ford and other major automotive industries are also trying to leverage this quantum computing for their various use cases of their manufacturing, optimization, and etc. Right? Especially pharma is another sector, healthcare sector, wherein which people are trying to this particular infograph you can see, especially the drug discovery or new drugs design. This is one of the field where people are trying from the healthcare and pharma sector to use the quantum computers. Now, India, in fact, when I was listening to the previous speaker, somebody has asked the question about which are the companies leading. I'm glad and proud to say that even our country is leading in the quantum sector. Government of India has taken the initiative to launch the National Quantum Mission a couple of years, 3 years back, wherein which they have identified 4 different sectors to nurture in the field of quantum computing in terms of quantum computing, materials, communications, and computing. So because of the major funding is given, and because of that, there are several startups and government entities, enterprise users, universities, investors, they're all actively contributing to the national quantum ecosystem in our country. You can see that there are various startups which are working in our country, QNU Labs or QPI or Quantum AI, like this, which are building the products from quantum computers, quantum communication related protocols, and etc. And government organizations are also getting actively involved. Universities are also actively involved in the ecosystem. Right? These are all the players which are contributing to the growth of quantum computing in our country. Quickly, I'll just show a couple of our works which we have done with our team. This is about one of our research paper that was published on dealing with the quantum aspects of high-dimensional conceptual space. Of course, I'm not going to deal or explain this in term because of the want of time. And then, again, we have another work dealing with decision making in cognitive paradoxes with the contextuality and quantum formalism, which was published in Applied Soft Computing Journal. Again, quantum inspired ensemble approach for decision making purpose. Then we have about quantum machine learning related optimizing the quantum SVM algorithm for a specific case of breast cancer diagnosis. And similarly, this is another work on dealing with the quantum computing as well as the homomorphic encryption in the cryptography algorithms. These are some of the works that our team has published. And especially those, if we have students and faculty wanted to convey to the community. So people who wanted to venture into the quantum computing as a career, they should first of all understand the fundamentals, acquire the proper skills, and then we can have a formal or informal education. There are a lot of resources and gain the practical experience thanks to the platforms such as IBM Qiskit environment, which is providing the practical experience. And of course, the forums such as this would provide opportunity to network with the professionals. And then above all that, let us always be curious to learn things. So this would be the pathways to having quantum computing as a career. So with this, I would like to conclude my presentation. Thank you very much for patient listening. And let me actually go through the questions that people have one by one.
Yes, sir. Very first question we have, what are the possible research areas in this field in India?
What is that? I could not see that, madam. What is the question? Can you repeat?
Yeah. What are the possible research areas in this field in India?
In India, actually, as I said, there is a lot of potential. Now, as I've shown in one of my slides, where you have the government agencies, startups, the academic industry institutes, they're all working together. There are a lot of opportunities, especially if you are from a computer science. Obviously, you can venture into either number one, post-quantum cryptography or quantum cryptography. These are the two different dimensions. Of course, you can work either of them based on your interest. Then, of course, we have on the quantum communications. This is another interesting area where in which you can try to build the protocols, then building the algorithms, then quantum machine learning, or solving various problems, use cases that are already there. So these are the various research areas. Similarly, if there are people from the sciences backgrounds, such as physics and all that, materials, this is another area where people are actively working. So there are n number of opportunities. I would actually suggest you to explore based on your fundamental background. So if you know your background accordingly, I can suggest. You can write to me. Yeah.
Yes, sir. Next question is that what were the X, Y, and Z in Q gates? And please explain the corresponding metrics also. Sir, will it be possible?
Yeah. So actually, I would actually do one thing. I will share my another lecture that is already there. X gate, Y gate, Z gate. These are all called Pauli gates. They perform certain transformations on the given input. So for each gate, there is a given matrix. So when you give an input, if I want an X operation, I have to apply the Pauli X gate in the form of Pauli X matrix. So each operation has its own meaning. It performs phase rotation. So the spin what you have seen is one will give you an understanding of what do you mean by rotation. So you can rotate it. So that is the objective of these gates. I will share my another lecture, or even you can have this recorded lecture sharing. So that would be, I think, make them understand.
Sure, sir. Sure. We will share. So one more question is that how core quantum is different from hybrid quantum?
Yeah, so this is another This is an interesting question. A core quantum, when I say an algorithm, I'm purely working with the quantum states. Given an input, I will transform or encode it to the quantum states and then perform with the quantum gates. What is the hybrid is? It's a combination of classical and quantum. Meaning what, the QSVM part, what I have shown here, there, it is a kind of an hybrid wherein which the entire computation goes through the classical pipeline, but for a kernel estimation, it goes to the quantum, and then the output comes back to the classical and then gets executed. So meaning what, you have a task to be done. Among that particular task, some of the steps would be executed by a classical computer. Some of the steps would be executed by the quantum computer. That's called hybrid.
Sure, sir. So one more question is there. It's Pamjot Kaur is asking, I presented my seminar on quantum computing. My teacher said that there are many environmental factors like heat impact the machine. How is it managed if I pursue my dissertation in it?
See, as an end user, so okay, I'll answer this way. Number one, we need to understand as of now the available technology, whether you are using as a student, whether I am using as a researcher or as a faculty, or an organization or an enterprise that is using the current day available quantum computers. We are all dealing with the noisy intermediate state quantum computer, meaning what we have now at the moment, quantum computers that are having the noisy environment, right? So in that regard only, if suppose I have a task for which if I have 100 qubits that are required, obviously I need to play with more number of qubits. That is what is the available state. But having said that, for a student, when you use the corresponding programming environment of Qiskit, you can always handle it through, your algorithm can manage this, the error that is coming in. That is one thing. The second thing, as I said, We also know that our algorithms are BQB algorithms, in the sense it has the bounded error. So you need to repeat the algorithm couple of times to reduce the error. So this is another factor that as a student which you need to take care when you are running your algorithms.
Same participant has one more question, sir. In portfolio analysis, is it a hybrid quantum or it will be a core quantum?
So again, when I say portfolio analysis, it's a specific problem. Now, for that particular problem, what is the algorithms that we are going to use? See, for a researcher like me, if I am using a machine learning algorithm, for that particular machine learning algorithm, so far what people are trying is, there are certain operations that requires or that can be optimized with the help of quantum, and hence we are dealing with the hybrid now.
Yes, sir. Next question is there, what are the various algorithms for quantum computing?
So as I said, the algorithms per se that is available at standard or the Grover algorithm, Shor algorithm, these are the fundamental algorithms that are there. Now on top of that, for a given task, as a researcher, as a community, it is our job or it is our task to run our own design our own algorithms. That is the reason why recently the Government of India DST National Quantum Mission call, there is an exclusive call for designing quantum algorithms. So if it is for healthcare sector, we need to design quantum algorithms. This is one of the area in which everybody is looking for, where hardware is progressing. Again, on the software side, we need to build the algorithms.
Sir, there is a last question, I hope, and the person has raised the hand. I request technical team to unmute her, Mittal, Dr. Mittal. Yes, Dr.
She's
Mittal, you can.
unmuted. Unmuted.
Yes,
she can ask her question.
Yes,
good
Dr.
evening,
Mittal.
sir. Yeah, am I audible there?
Yeah.
Yes.
Yes. Good evening, sir. Actually, I raised the same question in the previous session as well. Being a finance person, I mean, I'm a faculty of finance, and whatever things I'm observing as of now, like use of AI and use of this quantum computing for all the core operations that are being performed by finance professionals as of now, like portfolio optimization, construction, and so on. So most of the students in finance do come with a non-technical background. Now, in order to look at their future and make the students prepared for all these technologies, can you guide us on how to make sure that our students are prepared to take up with all this, specifically the students who are from non-technical background and pursuing finance career?
So yeah, as I've shown this particular slide, see, now it is all about whether I'm a finance student, whether I'm a computer science graduate, or whether I'm from whatever is my background. So now the point is that now if I say that I'm from computer science, I don't know what is meant by stock market. I don't know what is meant by portfolio management. Right? I should know at least the basics of it, or I should know at least the basics of or fundamentals of what is happening in the finance, right? I may not be a master. At the same time, the other disciplines like finance or marketing, people should know what is happening in the technological world. And, for anybody, I would actually suggest this particular pathway. Understand the quantum computer. Imagine that, what is my background? Imagine if I am from finance or from a different management or whatever is the sector, I should know what are the principles, right? I should know whatever is the relevant required skills for my this one. In the sense, if I know technology, that is fine for me based on my background. Okay, you can stop with that. In case if I am from a computer science, obviously you need to go for pursuing the formal education. Whereas a person from different domain of such as what you mentioned about finance, they may not have to actually look for pursuing the formal education. You understand the technology, you listen, you participate in the seminars like this. Similarly, interestingly, I would actually suggest, from the use cases what I have shown, you see McKinsey has given the use cases. You see the reports that are coming from the Boston Consultant, the reports that are coming from all other, the firms, which are leading consultation firms, they actually give any of this technology. I would suggest that they would give in a very lucid manner. See, take an example. I gave my presentation. I talked about qubit. I talked about the decoherence. I talked about representing the superposition in the form of linear combination of. But all this is not required, right? You look at their reports. They don't deal with all this technology. So especially if you are from a different background such as finance, I would actually suggest you to look at such reports coming from these consultation firms, which will give you a very lucid introduction to the technology, but you will understand what is happening and you will understand how it impacts. The slides that I have shown, the infographics that I have shown, they are from those firms, right?
Yes.
Yeah.
Yes.
sir.
Thank you so much.
Yes, sir. Sir, it's like you delivered the concept with such a clarity and simplicity. Like this is the most complex, we can say, the concept, and you made it very easy to understand and connect with it. This topic you simplified, that is the quantum states and superposition. Like it's with a visual example such as the clockwise or counterclockwise spin you have shown, that made it very easy to understand, and the participant who were new to this subject, that was for them also it was very easy, and it's not clarified the core concept but also sparked the curiosity to explore the quantum technology further. So thank you so much, sir, for delivering such a well structured and accessible explanation. Thank you, sir.
Thank you, madam. I'm glad that it is useful, because I'm glad that there are several participants still listening even after 9 o'clock, and it's good to see their curiosity. I am happy that it is useful to them. Thank you.
Yes, thank you, sir. Okay, participants, we have shared the feedback link over here. I would like to put over here 3 points. The attendance regarding, so in line with the AICTE norms, attendance will be mapped through the feedback system during each session. We kindly request you to presence across the session with at least 80% participation being the benchmark for the successful completion. There will be a final assessment that will be on the last day, that is 20th September from 6:30 to 7:30, and minimum 70% is the qualification criteria. And we are confident that your engagement throughout will make this meaningful exercise rather than a formality. Immediately after the test, the participants are invited to log into their ATAL accounts and complete the final feedback on ATAL account. And this is also will be during the 6:30 to 7:30 time period. The AICTE certificate will become available for download once test score are uploaded and the feedback loop is complete. The organizing team will communicate availability to you directly on the group. Thank you. We deeply appreciate your cooperation in aligning with these norms. Thank you. Team, we can end the meeting now.